Okay. So these two pictures. So the question is, is one of these like states evolving? So let's understand that. So a global multi-way system is more like I think it's right that the local multi-way system is more flexibility of the operators.
Yeah, isn't that what I said?
It is what you said, but I'm just trying to understand it. So let's go through it more carefully. So in the Schrodinger picture, the states evolve. In the Heisenberg picture, the operators evolve. I'm actually now confused for a second about the Heisenberg picture. So in the Schrodinger picture, you have psi of 0, psi of t, et cetera, et cetera, et cetera. Right? How does the Heisenberg picture work? You have O, the operators.
Yep, you have O of t, and then your states form a fixed basis for the Hilbert space.
Okay, so let's understand what the analog of that is here. So the Schrodinger case is states evolve. So what's the analog here? So in what sense? I see. So in a global multi-way system, we are considering, in what sense? Now I'm a little confused here.
What's the question?
You're claiming that a global multi-way system, we have identify states and look at how they change.
Yeah.
In a local multi-way system,
you have a fixed basis of expressions.
That's what I'm thinking, yes.
And then you look at how the events are modified as a consequence.
Right.
Right.
There's actually nothing new under the sun. So to what extent is this actually formally the Schrodinger versus Heisenberg picture, in addition to being qualitatively so?
I think completely. I even have a way of proving it potentially.
Okay.
In fact, we could even, if you want, do your favorite method of proof by compilation.
Okay.
Because within the quantum framework, right? Ruhi and I developed a way of translating between the Heisenberg and Schrodinger pictures.
Mm-hmm.
So we could just compile a system in the Heisenberg picture into the Schrodinger picture, or compile it into a multi-way system, then translate it into a Schrodinger picture, then compile that to a multi-way system. And what you should see explicitly is the difference between global and local multi-way dynamics.
Right. Fixed basis of expressions, but the events.
Which expressions get ingested and in what and in what order changes.
Right.
So the events are being updated.
But the structure of the events changes, in a sense.
Right.
Okay. Very nice. Okay. Another one down. Again, we should probably maintain it. Go ahead.
I know. I was going to say, and that has the nice implication that if this is true, then my local multi-way system should be the Dirac interaction picture.
Okay.
right? Where time dependence is carried by both sides.
Yes, yes, yes. Which seems about right. So this is the event global multi-way system. It's like the Dirac picture.
Right.
Question mark. We should be maintaining a better dictionary here. All these different things that.
We can add those to the glossary, right?
Which glossary?
To the physics project glossary. It would be fun if we just add, Heisenberg picture, and then we say, C local multi-way system.
Yes, but I mean that glossary. There's a thing in section 8 of my technical document, but there isn't another place that I'm aware of where we're maintaining these correspondences.
Right. Possibly something for Barbara.
I think it's a bit technically
maybe
complicated for that, but I think that yeah, I mean what we really need. We should bring this up. I mean, it's basically a page that has kind of known physical effects.
I don't even think we should restrict this to physics. I think we should have, to my mind, I think there's at least sort of 3 layers of translation we can do. There's, physics project, there's pure math, there's physics, and there's theoretical CS.
And there's biology, and there's economics, but
true. Although my impression is right now, at least, that the biology and economics analogies are not as well developed.
They're not as well developed, but doesn't mean they're not there.
No, of course.
Right, but okay, what would we structurally do for this? Okay, so what we've got here is, I mean, again, we're getting off track here, but let's just take a look for a second. In here, we've got this. This was the beginning.
Yep. Right, but like I said, I don't think that's. I don't think that's exactly what we want.
No, we need more than that, and we need what's that?
I think we need to have multiple layers of translation.
Well, first thing we need to do is okay, so we're going to call this, I mean, we say glossary, but there's also basically a dictionary. This becomes okay, where am I going to store this? This would be probably under writings.
It's again, I'd argue it's less of a dictionary and more of a Rosetta Stone, right? Because it's not translating from one language to another. It's translating between multiple.
No, I know, but the Rosetta Stone was merely a set of examples.
Right.
So I mean, the first steps in that are probably these things here. But each one of these can be expanded, right? So probably what it wants is, gosh, why is that spacing wrong? Grumble. Sorry, just a second. Okay, so hold on, let me just go there for 1 second. What is it called? SW Tech paper. Okay, so it's basically this section. Begins the dictionary. So I think what we need for that is, for each item, we need sort of the heading of what it is. And then, okay. So actually, it's a little complicated, right? Because it is translating into, this is all translating into our models, right?
Right, which I don't think is what we want. Or at least that wasn't what I had in mind.
Well, we want both ways, right? I mean, we want this, but we also want other stuff, right? I mean, what's an example of?
Well, like I say, my thought was it would not be a dictionary. It would be a Rosetta Stone. It would be something where it says, so what in WPP is known as a branch pair, in mathematical logic is known as a critical pair, in physics is known as a canonical commutation relation, blah 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 blah. It would just be a straight up translation of terminology from one field to another.
Try it, but I mean, like Schrodinger picture,
right,
is a physics term.
Mm-hmm.
So I mean, so the multi-way translation of multi-way systems.
So it would be, so it'd be in physics project is local multi-way system. In ordinary physics, it's known as Heisenberg picture.
Okay, so let's take an example then. What you're saying is, okay, so let's take the example of, but how are we going to organize these things? I mean, so let's take branch pair as an example, okay? So the question is the physics project the main thing? See, it's different ways round. You want it different ways round.
Right.
But so the question is, what in the actual document, what is the head word?
Well, why can't it be? Why can't it be a sort of Rosetta Stone structure where you can flip it around depending on what language you care about? Right. So if you're a mathematician, you can go to math view and you can see the translation.
Well, so you're saying it's simply a correspondence. So okay, so what we have is, okay, so it's a multi-way. I hate to use multi-way because that's a very confusing.
Polyglot.
Yes. Polyglot dictionary. Okay, so the items.
So the default might be physics project first, but then you can.
Well, but you see, but some of these things. Okay, but see,
some of them won't have straightforward translations.
They're not named things. Some of these things are not named. The rest frame of the universe. What do we call that in the physics project? See, in some places they have a nice
digraph embedding.
Yeah, but that's not for physics project. A layer digraph embedding of the causal graph.
Right.
But that's a weird thing to, that's not a crisp ba-boom thing.
No, some of them will be wordy, but that's inevitable. We'll make it as non-wordy as we can.
The point is that there's typically a field in which the thing already had a name.
Right.
Right. I mean, so like the Schrodinger picture.
But there are enough examples where that isn't the case that I think it's worth building this.
Well, no, I agree. I'm just asking about how it's presented and whether what happens is, I mean, to my mind, okay, so the question is, are there ever things which are crisp in the physics project and uncrisp elsewhere? Like branchial space. I don't know, that's mildly, what is the translation of branchial space? Who knows? I mean, it's a space of entanglements and things, but
it's pretty easy, I think.
I understand it's pretty easy, but that's a case where it's crisply said in the physics project and not crisply said elsewhere.
I disagree. I mean, projective Hilbert space is quite a crisp idea. Proof trees are quite a crisp idea. You know, group presentations are quite a crisp idea.
Yeah, but the question is, what's it actually going to look like when you look down it? The point is, if it has a thing, it's pretty easy to read something where there are head words that are some kind of crisp head words in a particular field.
No, I understand, right? But whichever field the point I'm making is whichever field we have as the preferred one, there will be some that are crisp and there will be some that aren't. There's no one field where everything is crisp.
No, I'm well aware of that. I'm just saying
so I think it's more important that we just have an ability to switch between views than it is to pick one that has the most crisp definitions.
I'm just skeptical. I have found that these things where you try and make a sort of computably modifiable piece of English exposition get very difficult. It's like writing, interactive fiction or something.
But in this case, you're not modifying any prose. You're just changing the order. You're commuting the order of columns in a table.
Well, it won't be a table. It's too big to be a table.
Okay,
but I don't think it will fit as a table. So I think it'll be, for each thing, it'll be, so let's understand what each thing will be. Each thing will probably be a box of some kind where it has a label that says, although you see, even in physics, there may be multiple. So in physics, there might be a, traditional physics, paren, general relativity, right? Might be just generic traditional physics, or it might be that there's a version of it in traditional physics relativity and traditional physics quantum mechanics, quantum theory, right? And then there'll be various kinds of mathematics. Well, so what you're telling me, what you're saying is that for each term, there's going to be a box, okay, in which there are labels for these different tags, and then there's a description.
Right.
Okay. And then the question is, what would you do? What would be the ordering of this? That this would be, you could reorder it, I suppose. I mean, these boxes could be arbitrarily ordered, actually.
Right.
Depending on where, and so long as they're color-coded, I don't think that will be a problem for people. All right, so the idea would be each box is ordered as it feels like. But now it's also useful to collect, I think, some the question is that this grouping into physics concepts, physics theories, and so on, we have to have some grouping. What's the ordering? Okay, each box is ordered as seems best, with tags and color coding for each quotes language. Okay, now what is the order of the boxes? Do you understand what I mean? What is the cross box ordering, so to speak? I mean, I would argue that this isn't completely stupid. This way of doing it isn't completely stupid. Anyway, so examples. So an example would be, so WPP local multi-way system. And then, so there may also have to be physics okay, so let's say we do that. Now, there's probably also has to be some explanation for each of these things.
Mm.
You seem very skeptical.
No, yeah, I agree. Yep.
So then each box would have a little bit, each box could have a pop-up for more discussion / references, etc. All right. Well, this would be I think this would be a very good thing to do with our research affiliates, to have some sessions just filling these in.
Yep.
Even ones without me. Huh. Okay, so let's boy, that's maybe for another colloquium-like activity. Creating the dictionary between okay. All right, let's go back to what we were doing here. So we were about to discuss, before we got sidetracked there, we were about to discuss the generational states business. And then, I mean, I've got several more things I would really like to discuss. I hope okay, hold on, let me just.
Okay, well, let's do it.
I know, I'm getting there. I'm just pulling up my relevant pieces of documentation. Okay, all right. Okay, so let's go here. Okay, so let me make some notes here. So the idea here is a global multi-way system. Let's see. So what we want to say here, what we want to understand here, this is more global than global, basically. A generational state, right? In a global multi-way system, you're aggregating. Yeah, I mean, generational states, global multi-way system still has a single event connecting states, right?
Yep.
Imagine that we want to have sort of quotes as many, I'm just writing this roughly, as many events as possible happening between what we consider to be states of the system, right?
Yep.
Now, what's the relationship between that and branching?
Well, I mean, all of it's the obvious relationship, right? I mean, all of the branchings that are due to space-like separated events that we were discussing earlier are modded out, and so the only branchings that exist are ones due to purely branch-like separated events.
Right. Okay. I.e., all space-like events are done between generational states. So the only ambiguity is genuine branch-like ambiguity. Okay. So now how does that relate to the classical states idea?
Well,
What's
those
the
are the classical states. Right? The generational multiway states are the classical states. They're the ones that you would assemble by superpositions in the regular global multiway system.
Well, they're consistently. Walk me through that. Walk me through that. How do we think about that in terms of GD6 and the multiway system?
Well, so a collection of GOD6 corresponding to the evolution of a snake state in the ordinary global multiway system is a superposition corresponding to a generational state. That's that's the definition of a snake state.
Okay, I have to remind myself how this all works. So
you have a global multiway system. You have
Yep.
a collection of states, right? That where the difference between them is a bunch of space-like separated events.
Right. So you can snake them together.
So you snake them together, you get a generational multiway state.
Yep.
So the point is, it's the snake states that you are seeing superpositions of, so when you perform quantum measurements, it's the snake states that you're collapsing, right?
Well, that are coming out of the collapse.
Well, no, they're the things being observed, and then the generational state
Right.
is the thing you see after the collapse. So the point is, the generational multiway states would appear in the ordinary global multiway system eventually anyway, but you can shortcut the process by performing a quantum measurement.
Right. Okay. So the point then is, okay, so the generational, i.e. snake states, are possible consistent states.
I don't think we should call them, I mean, the snake states are something else, right? The snake states are the constituents of the generational states.
I thought the snake state was a state which has a collection of states which can be put together.
Yeah, exactly. So each one of those is a snake state. They are, the snake states are a collection of states that are all pairwise space-like separated.
Yes.
And so when agglomerated, the snake states yield a generational multiway state.
Exactly. That's what I thought I meant here.
Okay. Sorry, I thought you were saying that generational states and snake states were the same thing.
Well, how many steps? Wait a minute. If you okay, you have to snake the snakes together, right, to make a generational state.
Yes,
generational state is
from a collection of snake states, you can derive a generational state, but the individual snake states are not equivalent to generational states.
Fair enough. Okay, possible consistent states that are formed from each other by doing maximal sets of events, that don't spatially overlap. Right? That's what we already said.
Right.
Okay, but so now, okay, what is the relationship? Because there are obviously multiple such choices of maximal sets of these consistent states.
Right. Each one corresponding to a different branch of the generational multiway system. up to isomorphism.
Right.
So each collection of snake states, each snake corresponds to a different possible GD-SIC in the generational multiwave system.
Okay. And bundles of those GD-SICs form the generational states.
Wait, what?
Look, if you're saying that the snake states correspond to, you go from snake to snake to snake along a GD-SIC, right?
Are we talking in the global multiway system here?
Yes, in the global multiway system.
Well, along a collection of GD-SICs. Right.
Okay.
Each snake evolves by a collection of GD-SICs in the global multiway system.
Fine. Yes.
And the evolution of that snake corresponds to a single GD-SIC in the generational multiway system.
Yes. But that collection, and then to get to a generational state, you have to aggregate a bunch of snake states. Right? You have to connect together a bunch of snake states.
Right.
So the picture is from a standard global multiway system, the snake states are effectively bundles of individual state GD-SICs, individual state evolution GD-SICs. Meanwhile, the generational states in the generational multiway system are bundles of snake state GD-SICs. In other words, they're GD-SICs in the generational multiway system, right? They're bundles of GD-SICs in the generational multiway system, I believe.
I think this is. I don't know.
What?
I'm not sure I like the way this is written.
Well, the words aren't very well done, but do you agree with the basic idea?
Well, the snake states aren't. Each snake state is not a bundle. Each snake state it's a state. It's a state in the global multiway system. So it's a single GD-SIC.
Oh, you're right. You're right. The snake states are particular states. Right. Are particular states that contain only spatially separated events, basically.
Right. And then, yes, generational states in the generational multiway system are bundles of snake state GD-SICs. Yeah, in the global multiway system, but I guess that's implicit.
But the snake states, to get from one to another, you're still going to have a whole row of events happening. Right?
No.
Well, you can have them happening.
But it's still gonna evolve one event at a time. There's no row of events.
Okay, but in the generational multiway system, there is a row of events.
But there aren't snake states in the generational multiway system.
Because they've already been combined.
They've already been de-snaked. They've been, yeah. Each node is a whole snake. There are no constituent parts.
Is it a snake or is it a super snake?
No, it's a snake.
Okay, let's go through this again. Okay.
I think maybe we're concluding that snake state is a bad name.
I don't think it's a state, among other problems.
Well,
I mean,
it is.
A state.
It is a state. It's a global multi-way state. But we should...
maybe the snake was a cute idea, especially with snakes on a plane and things.
Right.
But let's say what it actually is.
Yeah, I mean, I think we need to be clear about when we're talking about snake states and when we're talking about snakes, which are obviously different.
What? What's the difference in a snake state and a snake?
A snake is a collection of snake states.
Oh, for God's sake! Okay, then we're totally losing it. Okay, let's have some better names. How could a snake be a collection of snake states? That's crazy. Okay, all right. For the standard global multi-way system, what are we saying here? These are.
Okay, so the way I was using the terminal, I think we may have been using the same words in different ways, as is so often the case. So the way I was using the terminology was that, you know, the snake is the collection of space-like, you know, of states created by pairwise space-like separated events, right?
Okay.
And then each of those states is called a snake state in the global multi-way system. So then the evolution of the snake is the evolution of the individual snake states.
Okay. Okay, so hold on a second. So we're referring to, okay, so let's understand what the right terms are. The snake is a collection of space-like separated of states that can be snaked together because let's just say this precisely. Because, no, I don't understand. Because basically they can be snaked together because they involve events that are space-like separated. But involve in what way? Where did they come from?
Well, the creation events, the incoming events for each state are pairwise space-like separated.
Okay. Because that's a decent way to say it. Because the creation events for them are all space-like separated.
Right.
Okay. Okay. All right. So what would we call that if we weren't calling it a snake?
A brain?
What do you mean? A brain, B-R-A-N-E?
Yeah.
Why?
Because, you know, we only called them snakes because of the strings case where they'd be extended one-dimensional objects in the multi-way system. But in the arbitrary hypergraph case, they would be brain-like.
Oh, for goodness sake, that's even more obscure. I'm talking about something like spatially.
We could call them something really boring, like consistent sets.
Spatially consistent sets.
Yeah.
Actually, if we just had an N there, we could, you know. Spatially consistent state sets. AKA snakes.
I mean, snake isn't a bad term.
It's not terrible.
It's pretty evocative.
What do you think? Do you think that a snake, let's be clear, a snake has a nervous system which maintains, you know, where the events happening in different parts of the snake are connected, are time-like connected. Otherwise, the snake
something like that. Yeah.
Otherwise, the snake would be, you know, I mean, you know, the question is, are the ganglia in the snake operating independently?
Right.
But what does this mean? This means that the spatially consistent state sets. Spatially consistent, that's not even right. Spatially independent. Is that right?
What if we say maximally consistent state sets, right? Because you're basically asking what's the maximal collection of events we could apply without having conflicts?
Yeah.
Maximally consistent or maximally non-conflicting or something.
Maximally non-branching.
Yeah, although that's a bit confusing, right? Because they're non-branching in the generational system, but they're branching in the global system.
All right, let's go back to this ontological basis idea. I think, I mean, I more or less understand what's going on here. I'm not sure that this is the right way to explain it, but let's understand. Okay, so what we're saying is, imagine that we want to look at dynamics. Purely in generational states, right? What are the laws of motion for generational states, basically?
Right.
And the claim is that in generational states, there is still branching, right, between generational states.
Mm-hmm.
Okay, explain the relationship to the ontological basis and to the Bohmian idea.
Right. So in the Bohm paper he wrote with Hailey, this ontological basis idea is a way to say, let's have our Hilbert space be spanned by essentially a set of classical states. Then we have this, we adopt the standard, Schrödinger causal interpretation of QM. But the point is, when you perform a measurement, you necessarily collapse the wave function down onto one of the ontological basis states.
You mean, I see. You mean to say that the sort of the classical states already exist?
Exactly. And so when you perform measurements, you necessarily see classical outcomes, because that's
which is what you expect anyway.
Does.
Yeah.
Right.
Okay, so the idea of the ontological basis is that you consider only classical / generational states as basis elements. Okay, so we could do that too. So our generational multi-way system is like Bohmian evolution. Is that correct?
Right. Exactly. Yeah, so the point is that in exactly the same way, in the ordinary Schrödinger picture, you are assembling the classical state when you collapse down the superposition, whereas in Bohm's picture, the ontological states already exist and you're collapsing onto those. In the same way, when you perform a measurement in a global multi-way system, you are collapsing a bunch of snake states down to a single classical state. Whereas in the generational multi-way system, the classical states already exist. They're the only things that exist.
Okay, let me walk through that again.
So I think the correspondence is pretty direct.
Okay, so let me walk through that again. So in a standard global multi-way system, our interpretation of doing a measurement is a foliating through of different states.
Yep.
Now, wait a minute, but why hadn't we concluded that what you get is an individual state in the global multi-way system when you do a measurement?
Yeah, right. But the state that you observe is a state that would appear in the generational multi-way system. It's a classical state.
But there are many other states flapping around.
Right, but those are the ones that are being fought off by your choice of foliation.
I see. Okay. There are many states that cannot be quotes, classical observed states. Why not? Explain why not.
Well, because they would be produced by, if you know, by definition, if they're not generational, then they're being produced by a combination of space-like and branch-like separated events, or possibly purely branch-like separated events.
So what? Why does that mean that they can't be the result of measurements?
Because they're not classical. If they're produced by branch-like separated events, they're not classical by definition.
Okay. So in other words, the point is, they couldn't be, the other events contain contain the results of branch-like separated events.
Right. The other states contain the results.
Yes. Separated events, i.e., they mix sort of classical paths of history in some sense.
Right. So, yeah, so the point is all of those are ones where the observer is confused about what actually happened. And if we want the observer to be unconfused and to think something definite happened, then they have to observe a classical state.
Explain that. Why would the observer, okay, so they see a branch-like separated, an event. I see. Then the observer can't know. Well, walk through that for a second. Doesn't know what branch has been gone down.
They see two conflicting space-time events at the same point of space, right?
Yeah, okay, fair enough.
Which is a problem.
Right. They mix classical paths of history. So that an observer will see conflicting results at the same space-time point, i.e., the multispace, at that position in multispace, is thickened.
Right. So the operative definition of a measurement, at least in my opinion, should be one which gets rid of all such ambiguities.
Right. Measurement is something definite. Measurement is something which gives a definite result.
Right.
Okay, so now let's say that we look only at generational states, of which there are many paths in the generational multiway system. There's still different paths in the generational multiway system.
If you have non-trivial branching. Yeah.
Right. Okay. So now, how does that relate to? So the statement would be that in the generational multiway system, the states are states in the ontological basis.
Yep.
And then what's the statement about faster than light communication?
Well, this is where it becomes remarkably direct, right? So in the Bohmian interpretation, if you make a perturbation, then because you have some you have some pilot wave or some other kind of scalar field, if you make a perturbation to that pilot wave thing at some point in space, it can propagate instantaneously to another point in space and cause all kinds of non-local stuff. Well, exactly the same thing happens in a generational multiway system, right? Because at each evolution step, because you're applying a maximally consistent set of space-like separated events, if we perturb one part of the universe, that will change the set of maximally consistent space-like separated events you can apply. And so in particular, that perturbation can affect things instantaneously on the other side of the universe.
Let me walk through that.
Like, as though you're perturbing a pilot wave.
Right. Okay. So make a perturbation somewhere make a perturbation to a generational state. So the claim is that to maintain consistency, in maintaining global consistency, a change can happen. This can force a change anywhere in the universe.
Right. Let me see if I can cook up an explicit example. I forgot how difficult to understand these can get.
What are you looking at? Shall I look at your screen?
You can do it, but I'm currently just trying to show what happens if I perturb something, but it's not particularly helpful. I was just experimenting with generational multi-way systems.
What did Joseph do in his project? Did he implement a
what?
Generational multi-way for a hypergraph?
Yeah, right. That was his project in the end, right? He extended my code so that it also works for the hypergraph case.
Can we see a result then? Can we generate a result here?
Yeah.
Okay, what code do I need to generate the results?
Well, Wolfram generational multi-way system.
Okay, but what are these maximal match sets and things?
That's the same as the maximal match sets in my generational. I mean, so the way my generational multi-way system framework works is it calls on the existing multi-way system framework, but it gets what's called a maximal match set, which is this maximally consistent set of space-like separated events.
So you say generational multi-way system of, okay, and now
so
what?
My framework only works for strings and lists. So if you give it something like this,
okay, but he made it work with something else, right?
Yeah.
Okay, so we should show his results. I mean, if we can show those.
Right.
Okay. Okay, so what would his results be here? I mean, what is this here? Do you understand this well enough?
Yeah, like I said, this is a direct extension of the generational multi-way system.
So can I type something in so that I can get a picture of a generational sequence of generational states in a hypergraph system?
Yeah.
What do I type in?
Like I said, the generational Wolfram model function is what you want.
Oh, it exists.
Not in the function repository. It's not been integrated.
Okay, so where is the code?
In the community post, and it's the function in the community post that generates the.
So this is the community post. So where is the code?
I mean, it's there. It's in the notebook.
Okay, so which notebook? This notebook, or is there a notebook I download?
No, it's this notebook. Look, Wolfram model generational multi-way system.
I don't see it. Where is it?
In the thing in the thing that's subsection titled Wolfram model generational multi-way system at the bottom.
Okay, hold on. I'm not
Wolfram model generational multi-way system.
Okay, where is its definition?
The section above.
Okay.
But like I say, it depends on my implementation of generational multi-way system.
So you mean I can't run it or I can?
You can run it, but it requires me sending you some custom code. Well,
Okay,
it requires me sending you the same custom code I sent to Joseph.
could you send it to me so I can actually run it?
Yep. Let me.
What is the relationship between Max's max scan and generational states?
Well, I mean, again, my view on this hasn't really changed. It's the max scan is the analog of a generational evolution, but a single path generational evolution.
Fine. Okay. So,
I mean, that's basically what generational multi-way system does. Is it takes that algorithm but makes it more general.
I understand. Max scan for typical WMs, the single path Okay, so this is all paths of the generational multi-way system. So what you're saying is, I'm just trying to unroll the Bohmian idea. Okay, what you're saying is that in the full generational multi-way system, that branchings in the generational multi-way system associated with perturbations kind of, it'd be really good to see one of these generational multi-way systems that branches. I think we have some examples that branch, don't we?
Yeah, there are a bunch. I made a bunch in the documentation.
Of generational multi-way system.
Yep.
Pull that up. I assume that the students at the by the way, where on earth is the physics project stuff in here?
It should arguably have its own category.
I think it should have its own category, yes. Let's make that happen. Just send an email about it. Okay, so scope. So that is, what the heck is that? So these are generational multi-way systems that have multiple. The hell is that? Why is there an ABA? Oh, I see. It's two disconnected pieces. Okay. So there, I can even just say AAB. And now I will have a generational multi-way system. So for example, if I were to do that as an ordinary multi-way system, Oh God, this is confusing. Mm. How can we annotate these so it's not so unbelievably confusing?
What's the issue?
That this is confusing, that it's not clear. You know, here you've got, I mean, basically this, you're going to have ABBA and ABB, which is down there. How can I tell from this picture that those are the generational states?
Well, you can't. You need to see where the events are, and you need to check that they're space-like separated and maximal.
I know.
Algorithmically non-trivial.
Okay, but anyway, this is a branching generational multi-way system, right?
Right.
And so here, what you're saying is, if I were to perturb this state, the things that it could lead to here will involve changes that are completely global to the state, right? In other words, just because I change the A, what's that?
Right, exactly. I mean, so in an ordinary global multi-way system, if I perturb the left-hand side of the string, on the next evolution step, it's not going to immediately affect what's on the right-hand side of the string. It will have to,
right. Because what's happened is, and the reason is that what's happened here is this many events here, many space-like separated events here, have been conflated into a single thing here.
Right, by definition.
Indeed.
Mm-hmm.
So by picking that basis, you are forcing yourself to basically you're compressing time effectively.
Mm-hmm.
So by picking that basis, you're compressing time.
I don't quite know what it means to compress time. I mean, all you're doing is you're setting the speed of light to be infinite while maintaining a finite speed of entanglement.
You're compressing time in the sense that one step of the generational multi-way system can be, size of the universe steps.
Yeah, in the global
of the underlying system.
Right.
I.e., okay, so Joseph's thing, could we get a picture? Can we send me? Did you send me the code?
No, not yet. I mean, my generational multi-way system is a complicated piece of code. I need to. It's difficult to break it out.
Okay.
As a separate thing.
But didn't you do it for Joseph?
I did, but I didn't. I didn't save that. I assumed I'd only have to do it once.
Well, maybe Joseph has a page that has it on there.
I would need to download his thing from the notebook archive, and as far as I can tell, there's no ID for his, or there's no submission URL.
Wait a minute. Is this his notebook or is this not his notebook?
Well, that's his community post, which doesn't contain all of his code. It contains some of it.
Where is the link to his internal?
That's my point. I mean, so it was supposed to be the case that in the mentor evaluation that there's a URL to the notebook archive submission, but I can't find it here.
Well, let's ask Kyle.
Why
don't we send something to Kyle? It's part of the deal.
Do.
Okay, so is it in student profiles? If I say view student profiles?
Yeah. It's in student profiles under mentor evaluations. There's supposed to be a submission URL, but it just has a name. So I suppose I could search for it. I don't really know how to use the notebook archive.
sorry, where should it be? I'm mental
Measure
evaluations. Okay.
evaluations. Okay, I can't find it in.
Well, let's ask Joseph. Do we have his email address? It's right there.
Yeah, I communicated with him today about the RA thing, so I can.
Yeah, just send a mail. Why don't you send a mail right now, because I'll probably respond. Just say we need the code.
Yep.
Just can he send us the code that generates a generational multi-way system? Because I think what we should do here, I don't know what.
While we were talking, Alejandro just agreed to a JRA.
Okay, nice.
Yep.
I am totally confused by this data structure.
Sorry, what data structure?
Pay attention to what you're doing for a second. I'll deal with this.
No. Sorry, I've sent an email. What's the?
Okay, so in Joseph's post, what is this thing? Is this?
Yeah, it's a generational multi-way evolution.
And how does that relate to the ordinary? Okay, so let's take the same thing, just to try and prevent me being just utterly, flamingly confused.
Yeah.
Okay, so let's take that thing, and let's say.
Yeah, so obviously for the first 3 steps, it's going to be the same, and then for the 4th, it will only be one element of the 4th list there.
Right. Okay, so let's take a look at this. So then this is basically saying, so we could, if we had our state, this thing is basically saying, I mean, but this doesn't record as much information as the multi-way system.
No, because it doesn't have the predecessor states. So this is why it's going to take some work for me to integrate this into the generational multi-way framework.
I see. Splafferoo, why did that do the wrong thing? Oh. Okay, so here.
That looks like the last one. Oh, no, I can't tell. It could be any of them.
This one here?
What? No, I'm saying, so of the, obviously, you know, the big question is which in the 4th list, which of those elements is Wolfram model going to pick?
I can't tell this one here. This one here should be this one here. Is that the same graph?
It looks like it might be.
I agree that it might be.
Oh wait, hard to say actually. Yes, no. I can't do isomorphism testing in my head.
No, nor can I. I mean, we can count the number of nodes at least 6, 7.
Yep. Okay. on that we're okay.
Yeah. So it probably is that. But what this is saying then, okay, so let's just take this as an example, okay? So this is a generational, okay, so hold on. Let's take the analogy up here. If we did max scan, can we do max scan for the strings? We can, can't we? It's just substitution system, if I'm not mistaken.
I suspect so. I don't know. Yeah. It's
Okay, AAB, AB, ABA,
Oh, that's
BB. Yes. Okay, so that's that path there. AB. So in fact, in this picture here, we can simply say,
yeah. So it's going down 2 and then across by 2.
okay, hold on. Highlight graph, path graph, if I'm not mistaken, of this thing here.
Yep. So it goes straight down and then to the left
Why didn't that work?
because they're vertex styled. Do states graph structure.
Okay. Okay, great. So, okay, so that's the relationship to max scan of this. Okay, so now, go ahead.
I wonder if it's a coincidence that that's strictly the leftmost branch.
I don't think it is a coincidence.
Yeah.
I don't think it is at all. I think those are replace lists, and that's the replace list is always going to be. I don't think it's a coincidence.
Yeah.
Right. So
Neat.
okay. So then now, in the Bohmian world, in the world, okay. So the comparison between that and this. Right, only certain states here. So let's take a look at where are the generational states. So the generational states are, and here you are saying vertex list of this, right?
Yep. Ah.
What?
Matt Kafka has expressed interest.
Okay, good. Okay, let's keep going. Stay the course here for a minute.
Yep.
Okay, so those are the generational states within this system. Okay, so now what we're saying is when we make a change, just walk me through this. Just okay. The point is, I just want to do an example here where we say, let's make a perturbation. Let's say we start with AB, ABB.
Yep.
Okay. Well, actually, let's go down all the way down here. Let's start with whatever the hell that is. Okay, with this one here, let's just take that there. Okay, so let's say we start with this. Okay, so then we have a generational multi-way system. It starts with this thing here. You know, I have a feeling we may be proving the beta ansatz, so to speak.
Right.
That's a good name for that principle. Okay, so that's the case of. Okay, so now the claim would be we make a perturbation to this. Let's say we change the initial A to a B. And whereas, okay, so this now, oh, interesting. So you see what's happened here, right? So we've got things right on the right-hand side here have been changed.
Yeah, right. That's the point.
I know that's the point.
Yeah.
I know that's the point. I'm just trying to see it explicitly. Have we seen this before explicitly?
I looked at it a bit in the strings case back when we first looked at generational multi-way systems.
Okay, but so the basic point here is by forcing this consistency, we can have global effects. And well, that's basically Bohmian mechanics. That's the relationship to Bohmian mechanics.
Right.
Okay.
It's
Great.
neat.
It is very neat. How does it relate to the Hoofdian mechanics?
I do not understand that well enough to comment.
Well, we'll send a mail and we'll ask him.
But I mean, at least now I think we have a way of posing it that, he will be receptive to.
Yeah.
Because I know that Tuft is, he's an ontological basis kind of guy.
Right. Okay, that's great. All right, can we go on to the next item?
Yep.
Okay, I want to go back. Well, let's keep going with quantum for a bit, or should we go back to the okay, what did we do? What happened with the quantum harmonic oscillator? Can we remind ourselves about that?
Yeah.
The claim was that we needed to do that homework again, so to speak. So
which homework?
How the quantum harmonic oscillator works. I'm just looking for my material here. Hold on one second. So what is this? Is this your? What is this? This is your quantum harmonic oscillator, right?
Right. Well, actually, this was me trying to explain how phase works again, because there was still confusion about the nature of destructive interference, which I hope I have now clarified.
So wait a minute. That was okay. So hold on. There's another thing here, which is destructive interference.
Right. So, I mean, given that there was confusion about that both in Hatem's project and in Patrick's project, I decided it was probably worth clarifying once and for all.
Let's go through that, please. Okay, so hold on. Let me first of all, let me move this notebook. Let me move that notebook to the working material area. Which I think makes sense. Hold on. And let's rename it. Instead of QM notebook, let's call it let's rename it destructive interference. I'm going to call this one destructive interference -01-JG. Let me just check this. Yeah, okay. Okay, so let's open that up. Okay, so now explain destructive interference.
What, from the start? Or...
Yeah, try it from the start. Since now it should be. I mean, using what you have here.
Okay, I mean, so most of that introductory. I mean, the main thing are these numerical results because people kept, for some reason, not believing what I said. So, obviously the idea is the same as it always has been. So phase is a measure of the proportion of branch-like separated to space-like separated events. So then if you...
Wait. Branch-like separated to space-like separated?
Yep.
Why are you saying that? I mean, phase...
So if you...
I don't understand that point. You go ahead.
So if you have two geodesics in the, through the global multi-way system, if every pair of events is strictly space-like separated, then there's a phase difference of 0 between them, right? There's nothing quantum going on there.
Yes.
Right. If every pair of events is strictly branch-like separated, then it's like they're kind of maximally distant in branchial space. So
that's a
that
nice way
corresponds
to think about
to a
it.
phase of pi by 2.
That's very nice. That's a nice way to think about it.
Mhm.
That's nice.
Right.
So, okay, so basically phase, okay, so let's make ourselves a little notebook about destructive interference.
Yeah. So strictly speaking, whatever it is, the tangent of that of the phase gives you the ratio.
Have we? Oh, well, anyway, that's nice. That's nice. That's good. Okay, so let's say, okay, so that idea that I thought we had always had, I mean, that's where you actually have a position basis going on as well, which we haven't, I don't think we've discussed that properly before. Phase, the claim is, okay, phase is related to ratio of branch-like to space-like causal,
Well, separated events.
right, but branch-like to space-like causal edges. Well, it's not causal edges. It's these edges. What do we call these edges?
Events.
Okay, but we could also call them
Evolution edges.
Yeah, evolution edges, aka events.
Right.
Okay.
Related by an arc tangent, if you really want to be fancy. Right. So then the point is, okay, so if you have purely space-like separated events, then you don't need to apply a completion because you don't, as long as you don't have superluminal expansion.
Okay, so space-like events, space-like separated events need no completion.
Or to put it another way, if you perform a completion, you're not losing any information, right? Because you.
I understand. I understand.
Whereas if you have branch-like separated events and you apply a completion, you do lose information because you lose the information about which branch you were on.
Right.
And so
well,
the argument
need a merging of some kind, need a merging or a completion.
Right, which therefore destroys the which path you took information.
Right.
And that's the destructive interference. So how much information you destroy is therefore dependent on the phase, and therefore gives you how much, whether you have constructive or destructive or a combination.
Nice. That's very nice.
Yeah. So then what I was trying to show was, so that immediately makes this prediction that if you have, so suppose you induce a phase difference between two branches, and then you perform a completion. If the phase difference is, some multiple of pi or something, then you should get perfect destructive interference, which would basically mean that the state path weights for particular states characterizing the two branches should converge to 0. Whereas if they align, so they constructively interfere, then they should remain stable. Yep. So that's what these path weights are showing.
Okay, so hold on a second. I think this point I had not understood with this clarity before, that destructive interference is basically associated with the merging of branches.
Right.
This was really right. Is that really right? You're saying that the classical maximum in the diffraction pattern involves paths. I don't understand this. I don't understand. I'm now confused. Well, let me see an example.
Okay, so the point is, okay, so if we look above, you can see the way that we can induce a phase difference, right? So you have on the left here we have our ABX state, or again, actually let's look above, right? So you have ABC and you have DE on each side.
Mm-hmm.
So in one case you have 3 events, updating that branch. In the other case you have 2 events, and so that gives you a periodicity and hence a phase, and you can see that phase difference because there is, because you have there are events acting on 3 characters on the left and 2 characters on the right. That means that exactly 2 pairs of events will be space-like separated, and exactly 1 pair of events will be branch-like separated.
Okay, so let's talk about, if we were to assign a phase to this state, what would it be?
You mean a phase difference between the 2 branches?
Well, you mean between this side and this side?
Yes.
Right. Well, fine, but we'll just arbitrarily pick this to be 0, phase 0 over here.
Okay.
Okay, so now let's work out, if we assume the left branch, the left bottom state has phase 0, the phase of the right state is what?
Pi by 4.
Because it has a pi by 4? Why not pi by 2?
Sorry, pi by 2.
Okay. Okay, because it has a single branch at the top.
Right.
Okay, so let's imagine.
Well,
okay.
But crucially, I mean, the important thing is that there's exactly 1 pair of branch-like separated events.
Yes. Right. So within the phases of relative phases of these guys here will be 0. These are all the same phase. Correct?
Right. Well, I mean, yeah, because there's only 1 branch.
Exactly. Okay, so my question now is, okay, so let's get destructive interference in this creature, which this is not. This is pi over 2. I want to see pi.
Right, so that's what I did below.
Okay, let's take a look. Okay, so where are you doing that?
So this is obviously perfect constructive interference. You have an AB and a CD.
Where were you looking? Sorry, this one here.
Yes. So this is post completion. So you have 2 branches, A, B, and CD. And if you
wait. This has been forced. Okay, now we do completions to force causal invariance, basically.
Right, but to force causal invariance, crucially in a case where you have a phase difference of 0.
Right, but here we have phase differences everywhere of 0.
Mm-hmm.
Okay.
And so you can see then post completion, all of the state path weights go to a quarter and remain stable.
Okay, fine.
And you can see that numerically below. So that's what you'd expect from a constructive interference case, right? From a phase difference of 0.
Well, all the states have phase difference 0, basically, is what you're saying here.
Yes, and so in particular, you don't get destructive. You only have constructive interference. All the path weights, remain stable.
Yes, right. I get it.
Okay, so then below, here we now have the ABC to DE case post completion. Okay.
Yes.
So then that's now a destructive interference case.
Okay, so why is it destructive? Why isn't it pi over 2? This defines a pi over 2 difference.
Right.
So and then there's more pi over 2 differences here. Or are there not?
Well, this is post completion, so it's a bit complicated to explain what's going on after you perform the measurement.
Okay, so wait a minute. Here we start with a pi over 2 phase difference between ABC and DE, right? Right?
Hang on, wait. Let me work this out. You've now got me worried about whether it's pi or pi over 2. I think this might be pi.
I need a piece of chocolate. I will be right back.
Yeah, okay. Yeah, this is right.
Hello, sorry.
Hey,
Uh,
sorry, yeah, this is right. This is a phase difference of pi, not pi over 2. Sorry, I got it. Yeah.
explain why.
So because so obviously the backstory to this, if you scroll back up to the top of the notebook, so the reason we've discussed this a couple of times, I think. So the this idea of laying out degrees of freedom in space rather than in time. So if you scroll down, there should be an example of somewhere a little bit further down. Yeah, okay, so like here's a periodic system. We have A goes to A B on the right, and C D on the left. So
All
those
right,
are both
this one here.
no, just above it.
Okay.
On the right, A B. On the left, C D.
Okay. Yep.
So there's period. So the right branch has period 2, and the left branch has period 2. And you could also have the right branch having period 3, where you had ABC, ABC, or something.
Okay.
So the point is, you can then lay that out rather than laying it out in time. You can lay it out in space. So there, just below it, we have the left branch being the single string AB, and the right branch being the single string CD. So you're replacing
Okay. Right. Okay. So this is temporal periodicity. This is spatial. Okay, so this is the temporal case.
Yep. So that's a length 1 string with temporal periodicity 2, but which we can simulate instead with a length 2 string of temporal periodicity 1.
Right. Okay, so then this one.
The same.
So here, if we do this, let's just look at the evolution graph. Right. The path weights will be different, though. Correct?
But they'll normalize to the same.
Okay. Okay.
Right. Okay. So the point is, we're using the length of the string as a proxy to the periodicity, and hence to the phase. Right.
What's the phase part of that? Where did the phase come into that?
Well, this was the conversation we were having with Patrick and Kyle about. So they were saying, take a cycle to be an eigenstate, and then its temporal periodicity gives you its phase. And the point I was making is that that's equivalent to, almost trivially equivalent to collapsing that cycle down to a single state, saying that that's an eigenstate, where its phase is given by this ratio of branch-like to space-like separations.
Phase in the ordinary quantum mechanics sense.
Yes. Right.
But I mean,
okay.
I don't understand how you get phase in this case. Phase in our sense of where you land in branch field space.
Well, this was my point, right? So Kyle and Patrick were using conventional quantum mechanical intuition, where phase is given in terms of temporal periodicities, and I was trying to show a way you could convert that into our scheme.
Okay, fine, but let's walk through that for a second. Okay, so what we're saying is, I'm confused here. So how do we work out phase in this case? What do you claim is happening with phase in this case?
In that case, it's just phase. I mean, it's just ratio of branch-like to space-like separated events, which in this case is...
What is the phase of that state? What is the phase of that state?
The phase difference is 0.
Okay. Because there's no further... Why is that phase difference 0? Why is the phase difference not pi over 2 from that initial branch?
Because the ratio of branch-like to space-like separated events is 0.
Because this is a space-like separation.
Right. So because you could pick, say, the event that updates the C, and the event that updates the B, and the event that updates the D, and the event that updates the A, and those two pairs are strictly space-like separated.
So these are these have zero branch shell separation.
Right. And that is analogous to saying that the cycles A B, and CD have the same periodicity and hence have no phase difference if considered as eigenstates.
Right. The output has zero branch shell extent, so to speak. Only spatial extent. Okay, I understand. All right, so let's keep going here. So now...
Right, okay, so that was just how I was converting between their formulation of periodicity, of phase in terms of periodicity, and my formulation of phase.
I don't understand why phase in terms of periodicity has anything to do with anything here.
Because of ordinary quantum mechanics, right? Because that's if you have an eigenstate with a certain periodicity, you can that gives you your e to the I. H.
I know that's the interpretation of that.
Theta.
I don't quite understand that here, but okay, fine.
Which.
No, I don't understand. I'm concerned because we have a notion of phase that is associated with position in branch shell space. And I don't understand how the notion of phase for the e to the IHT temporally generated phase in quantum mechanics, I don't understand how that relates to position in branch shell space.
But that's exactly what I'm describing here. That was the whole point of this conversation, right? I mean,
okay, but what I would expect here is that the phase would zigzag back, that these states would zigzag back and forth in branch shell space. That's what I would expect, given that it is going, that the phase is, is an initial phase of whatever it is, whatever, and then it has period 2, so that, it's like a -1 phase each time. Right, but that would suggest to me, in our interpretation, that C and D zig and zag back and forth in branch shell space. Am I wrong?
Sure. Right. But I'm giving you a coordinatization.
Where are you giving a coordinatization?
I mean, this is my definition of phase. That gives you the coordinatization of branch shell space.
No, I understand, but in this case here, okay, where you're saying there's a phase, the phase is the coordinatization of branch shell space. In this case here, where you say, then what should be happening on this branch here is that in branch shell space, C and D go zig-zag, zig-zag. So if you were to capture just a C before you get to the D might have phase difference 0 from the S, but the C does not have phase difference 0 from the S, following the standard laws of quantum mechanics.
Yeah.
Okay. But how do you get the coordinatization in this case?
By converting it into something with spatial periodicity and then doing the standard calculation.
What do you mean by standard calculation? You
Taking the ratio of branch-like to space-like separated events.
Okay. So in this case, we have 0 branch-like separated events. So how do we get phase out of that?
Well, there's 0 phase.
Okay, but there isn't 0 phase here.
Yeah, there is.
No, not between C and D.
But C and D are part of the same eigenstate.
So you're saying you can't coordinatize this. You don't know. Given this, you don't know what the phases are.
They exist at a single. They have the same coordinate because they're the same They're part of the same eigenstate.
In this case here.
Right, but you can ask about the difference between the coordinatization of CD and AB. But in that case, it's 0 because there's no phase difference.
I understand, but you're saying that this representation gives us no information about the relative phase of C and D.
Right.
Okay, fine. Fine, that makes sense to me. But I mean, in order to get the right interpretation here, C and D, there might be some other way of deducing where C and D are in branch shell space, and they got to be zigzag, zigzag, back and forth.
Sure.
Right, because otherwise you have not got the standard quantum, sequence there.
Mm-hmm.
Okay, let's keep going. I think.
Right. Anyway, so the point I was making is that therefore, in our case above where we have periodicity 3 and 2, the additional periodicity of 3 corresponds to an increase in pi, an increase of the phase by pi.
Why?
Because you're taking the period 2 state and you're extending it by 1/2.
Why does that have a phase difference of pi?
Because 1/2 of a cycle is pi.
Okay.
Right. What you have 2 eigenstates, one of which has a longer period by a factor of 1/2. So therefore, you have a phase difference of pi.
Okay, let's walk through this more carefully again. Okay, so your claim is that these 2 branches have a phase difference of pi.
Yep.
And so therefore, where is the destructive interference here?
Right. I mean, so that's, if you go back to my other notebook, I mean, you can already see it here in the path weights, but I should, if you go to that specific example of that measurement, right? So we looked at the uncompleted version, right, where you just had 3 and 2. Then if you look at the post-completion version here,
Yeah.
and then you look at the state path weights, you can see that the state path weights corresponding to A, B, C, and D, E converge to 0.
Let's look at this more carefully. This is very nice. Let's look at it just a little bit more.
Well, if you look at the numerical results, it's much easier to see.
Okay, so this is, so what do these mean?
These are the state path weights. So at step 5, between
those
at
are
each
step numbers.
Yes, so at each step you can see how the state path weights are changing, and if you track the state path weights for A, B, C, and D, E, you can see they're converging to 0.
Okay, ABC
is 68 over 625.
Okay, hold on.
DE is 101
Okay,
over
I want to see one more explicit thing. I want to see a wiggle. You know what I'm saying? I want to see. Okay, we should be able to lay this out in space. We should be able to get a diffraction pattern. Right? This has spatial differences, right?
Mm-hmm. Right. You have a string position basis.
Right. So why is this not? If I look at,
it should already be laid out in lexicographic order. So
that's what I think. Right.
You could just list line plot it.
That's what I was thinking of doing, but I want to pull out step 5 here.
Mm-hmm.
How do I do that?
I don't know, select first of first equals.
Yes, 5. I can do that. That path I can do. Okay, so let's look at, let's actually say group by percent hash 1, 1 ampersand. And then for each of those, what we want to do is we want to pull out, assuming it's all nicely lexicographically ordered, which I think it will be, for each of those, we simply want to pull out the values of all of them. So okay, so there are weights. So now, for each of these, actually, what we really want to do is we want to, well, let's just look at the last one for a moment here. Oops. Splafferoo. What the hell does that mean?
Who knows?
Well, when in doubt, run more steps. See whether it resolves. But I mean, what do you think that should mean? That means that is in the lexicographic basis, so to speak.
Mm-hmm. I mean, I'm not. I should say I'm not convinced that any of the these list line plots. I'm not convinced that any of them are actually have any physical meaning, because we don't have. There isn't an obvious notion of space here.
No, but there's an lexicographic order.
Right, but whether that corresponds to anything physically reasonable, I
no, we have no idea. We have no idea. Why didn't this work? List line plot values. Well, what would it take to do? What the hell does that mean? What would it take to have something which has some meaningful spatial extent?
That was, I mean, that's.
Yep. Yeah, go ahead.
No, I was going to say, I mean, that's kind of what we wanted Hatem to work on, or at least what I wanted him to work on, right? Was reproducing this where you have both space. Because I mean, here, I set this up only caring about the branch-like stuff. But to reproduce something like a diffraction pattern, you actually want a combination of space-like and branch-like stuff. Because the two slits are both space-like separated and critically are branch-like separated, because that's how you get the diffraction.
Right.
So you need to have both notions.
Right.
But this, yeah, I mean, I agree. This has a notion of spatial separation, but it's very hard to interpret what that notion is.
I agree.
Physically.
Yeah, I agree. I agree. But I think it's sort of, I mean, it's amusing that this wiggles.
It looks sinusoidal, but I have no idea what that means.
Oh, who knows? I mean, who knows? Okay, so the next thing was the quantum harmonic oscillator.
What? Right. So yeah, I mean, so just to finish this thought, I mean, so the point I was making was, if you look at the ABC and you look at the DE, you can see that those values are converging to 0. Whereas above, where we had the AB and CD case, we saw they converged to a quarter. So there was constructive interference there, but now there's destructive interference because of the pi phase difference, right?
Yes.
And then below that, in the QM, in the destructive interference notebook, then I have the case where you have ABCF and on the left and DE on the right, and there you get constructive interference again, showing that you do in fact, if we take the case where you have pi and you add another pi, you get back to constructive interference, as you'd expect.
Okay.
Which I thought was kind of nice.
It is nice.
Anyway, so that's the sanity check.
Oops. What did Hatem end up doing?
Well, they produced some nice pictures of path integral interference.
And how does that specifically relate to this? Let's just try to understand that interference for a second, okay? In other words, could we actually get one of our systems to just look exactly like that?
Well, I mean, yeah, again, that's what we were hoping, or what I was hoping would happen.
I know, but let's just look at it for a second.
We got...
Using a beta ansatz.
We got sidetracked, whatever the phrase is.
What the heck is this? This is something yet different. What is that?
That's a local multi-way system.
I can see that. But what is it doing there? Other than hanging out. Okay, so this claims to be double slit in a global multi-way system.
Right. Except again, this is the one that I produced. So this is one where you just have branch-like separation, where the branch-like separation is the only one that matters, so to speak. So what I was hoping for was something where you would have, and I think you can only do this in the hypergraph case. I don't think there's a straightforward. No, actually, maybe there is a way you could do it in strings, but something where you have two slits that are both spatially and branchily separated.
Yes.
And then you have something that propagates through one or the other or both.
Yeah, I get it. But now what is this, and can we learn anything from it?
I mean, this is just, well, to the extent that I understand what happened here, it just seems like standard numerical QM, right?
I understand that, but it's nice and clean, and I mean, the what is this? So this is okay. But just to understand what the actual path integrals are, because what is that picture to me seems relevant to our pictures here. Can we just reproduce that picture basically?
Mm-hmm.
How does that work? And what are these things here?
Particle trajectories.
I think we have to ask Atom. All right. Yeah.
I mean, aren't they just what they seem to be? I mean, aren't they just sort of?
Yes, but they have phases. Each one has a phase. And the question is,
And
that's the whole.
Yeah.
Go ahead.
No, please.
Well, the question is, in this picture, right, is the phase combinatorially deducible?
Mm-hmm.
You see what I'm saying? If it is, then we can potentially make a mapping to that. If the phase requires geometry, then it's more difficult.
Right. But my position is still that we should just try the obvious thing of just, set up a double slit experiment and then see whether the phases you get by this ratio argument are the same as the phases you would get by geometry.
Yes, to which I suspect that they will be.
One would hope.
Yeah, I think that's some. So the real issue here is, just to record my thoughts here. Getting phases geometrically versus combinatorially. Okay, quantum harmonic oscillator.
Yep.
Anything to say there? What do we say? What was the conclusion there? How do we get the quantum harmonic oscillator?
Right. I mean, so obviously, I think we may have chatted about this before. So Patrick and Kyle had developed this scheme in terms of these temporal periodicities, but then ran into these difficulties with the ladder operators giving the wrong energy values, which was basically because of the fact that it's hard to do, when you have periodicities like that, it's hard to do energy determination because your causal edges tend to grow more rapidly than they should, because it's no longer the case that each eigenstate corresponds to a single state, but actually corresponds to multiple states.
I know.
Doing energy determination is non-trivial. And so that's why I suggested instead laying the things out in space rather than in time, so that then you can do simple causal edge counts. And I think at the end of his community post, Patrick says that's the next step, is to look at that case.
But so let's okay. So then the question is, okay. Okay, so naive thing, you can do it with strings, right? Do it with strings. Most obvious thing is to have different harmonic oscillator, have the harmonic oscillator to reproduce the time dependence of the harmonic oscillator.
Yep.
With something bouncing backwards and forwards on a string. Okay, so that, but with this, it is difficult to assess energies. Why? Why is it difficult to assess the energy?
Because each eigenstate doesn't correspond to a single multi-way state.
I see. Because eigenstates of the harmonic oscillator
are collections, are individual cycles.
Right. The harmonic oscillator are cycles of states in the multi-way system. Why can't we look at the cross-cycle causal edges?
We can, but I mean that's I think that was basically the problem that that Patrick was running into was how you do that.
Is it not obvious? Okay, so that's his states graph for. Okay, so let's look at the why do we say that is the cycle an eigenstate? I think the cycle is an eigenstate. The whole cycle is an eigenstate.
Right. But I think so. So he had some conceptual issue with the fact that you could traverse the eigenstate, you could traverse the cycle again, and you'd get more energy or something. But I think that's not an issue.
It's not an issue.
It's
not an issue.
Part of the yeah.
But so how do we compare the energy? Let's look at that cycle, and then let's look at another cycle, and let's compare the energies of the two cycles.
Yep.
So there's a cycle. Now let's look at another cycle. And let's ask whether the total amount of juice, so to speak, in the cycle, is that associated with the energy of the cycle?
Mm-hmm.
What do we think? Is that
I think so.
Yeah, I would think so too. So how do we get? So all we have to do here is add more A's. It's a sheep problem. Okay, so we just added some more A's to the sheep. And
we got some more orange.
Yeah, we got some more orange. The sheep are more lively. Okay, so now how do we think about that in terms of, in the harmonic oscillator, what are we doing here? What by adding more A's, what are we doing? I mean, we might think we're increasing the size of the system because the B will take longer to go around the cycle, right?
Mm-hmm.
Which would mean that getting more energy, well, it's a little bit complicated, isn't it? Because we're getting more energy. What is the energy actually? Because the energy, it's the, okay, first of all, where are the space-like, is all that energy propagating through space-like hypersurfaces or not?
Yeah.
Because there's no momentum happening here. Is that true? It's not obvious to me. But my question is, how do we get what was their idea of ladder operators? How do you get the ladder operator?
That I'm going to have to go back to. Oh, yeah, okay. It was so it's the obvious case, right? Your creator operator is just a thing that says A goes to AA, and your annihilator is something that says AA goes to A.
Sorry, I spaced for a second. Could you say that again?
It just increases increases or decreases the number of A's, right? So A goes to AA is your creation operator, and AA goes to A is your annihilation operator.
Okay, so A goes to AA is a creation operator. AA goes to A is annihilation. Okay, so now what will we expect happens? So we would expect, what is the standard result? It's a square root of, what is the standard result?
Square root n plus 1.
Is what? Is the weight of the state.
Yep.
Okay, can we see that at all here?
Yeah, so that would imply that the different, the pre-factor between the number of causal edges is square root of 3 or square root of 4, whatever.
Well, but so we can just compute the number of causal edges here, right?
Mm-hmm.
How do we do that from a graph? From the graph easily?
Well, you could just extract the causal graph and do length of edge list.
Okay. Isn't it just edge count?
That probably is a function, yeah.
Okay, so then let's put in here, let's just be programmatic about it, and let's okay, so now we have to say table that n goes up to 5, let's say. Splufferoo. What does that mean? Let's make sure we're not doing anything wrong by just doing this. What? Why are there more causal edges if I keep going longer?
Let's see the causal graphs in that case. Oh, that's why.
Why? Oh, because we need to do a simple graph on them.
Yeah. I mean, it is, yeah, that is correct. It is a cyclic. It's just adding 4.
Yeah, what do you expect it to do? Let's see.
Yep, that looks pretty 4-y.
Yeah, it does, but that's linear. What is
Yeah.
that doing? What is it doing? It's adding, so for every application of the creation operator, let's walk through this for a second. For every application of the creation operator, we are adding to the energy.
But wait.
This is correct. Go ahead. The harmonic oscillator has evenly spaced energy levels.
Right. So the ladder operator thing, that's also adding causal edges, right? Because we're not just adding A's, we're adding a rule that says A goes to AA. that will produce new events and also new causal edges.
All right, so the main point about this is it says that the energy.
I mean, yeah. So this is showing, as you say, the correct result that the energy levels of the harmonic oscillator are evenly spaced. The ladder operators are introducing another layer of complexity because the action of the operator itself is producing energy or has an energy contribution.
Okay, so let's look at one of those. So then what we're saying is in this picture here, right?
Yep.
The ladder operator which is A goes to AA, is the positive ladder operator.
Yep.
It's otherwise known as A dagger.
So that's adding a lot of stuff.
So God, this is such a complicated business. We are very lucky that quantum mechanics is visible just essentially combinatorially from multi-way systems. It's again another very unexpected thing. That quantum mechanics has that level of robustness, if you see what I'm saying. I mean, it's sort of not surprising.
Yeah, and actually, I think due in part to Xerxes' project, I now finally understand why it's the case.
Why? What's the case?
Why both relativity and quantum mechanics are such generic features.
Yeah.
One of them is quantum mechanics is a consequence of univalence and topology, and relativity is a consequence of cohesiveness and geometry.
I need to understand that better. Okay, so let's look at this edge count then.
But you need to get rid of the string repeat.
Why?
Oh no, I get. Well, I don't know.
No, I want to get rid of it completely, right? I'm going to get completely rid of it. That's just this, right?
Right.
But that 50 isn't right anymore.
Yeah, it's going to make a difference how many times you apply it.
So I think what we want to say is that's a T there.
Right.
And then we want to say that T goes to 5, N goes to 5.
Well, there is no N anymore.
Good point. Okay, what the heck is that doing?
There's no A's. There's no A's for the ladder operator to act on.
Oh, I have to put an A in there. Oh my God, what's it doing? What the hell is that? Okay, what is the interpretation of this? I mean, this is a free-running ladder operator that's just going amok. Right. It's not like it's being constrained to run only once and things.
Right.
So I think the ladder operator waits for another day, so to speak.
I mean, I think but yeah, there's definitely interesting stuff to be found there, and Patrick and Kyle at least claimed to have found some recursion relations for it, which were right up to a square root.
Yeah, but that's not right.
Yeah, well, we need to decode it.
Right. Okay. Question. It's probably getting very late for you. The things that I'm most excited. God, we got so much more stuff to look at here. I wonder whether what I'm doing is the right thing to do, because I mean, essentially, this is in part a. I mean, this is going to be a long blog post, full of beta ansatz, so to speak. I mean, we could break it up into many separate bulletins, but that's silly because then that's sort of stealing the thunder of these actual projects, which hopefully will come to more definitive conclusions. Could you just, as a preview, talk about the Xerxes thing for a minute? Because I'm really excited about
that. Okay. What would you like to know?
Well, I was trying to understand the univalent foundation stuff, and my understanding, you know, in the end, it seems like the key observation of the univalent axiom is that which is equivalent is identical.
Yep.
And that conflation of objects is claimed to be the thing that lets you slice basically that allows mathematics to be understandable and also allows physics to be understandable. That's the claim.
That's what claim?
Well, that was a claim of my thinking about this. Okay. So here's the claim. So consider mathematics, okay? It's full of irreducible crud, right? But yet the mathematics that we slice out seems surprisingly understandable.
Yeah.
And so the claim would be that essentially the axioms of set theory and the univalent foundations, which aren't the same, but they are related, are essentially making the statement that, that which is equivalent is identical, and that type of conflation of things somehow is what allows you to take out these slices that are reducible. And same idea.
Right, obviously. I mean, so the Rullial space is the free topos of all possible mathematics, right? It's the free group with no relations.
Yep.
The axioms of different branches of mathematics corresponds to sets of relations.
Exactly.
And it's the univalence axiom that therefore allows you to go from that set of relations to a corresponding fibration of the Rullial topos.
Wait a minute. I didn't get the fibration part. What's the fibration in this? What is the significance of a fibration?
So if you take a Rullial multiway system, then you can look at a particular multiway system, which would correspond to a particular field of mathematics.
Indeed.
And
well, I mean, no, not a particular Rullial, a particular multiway system in the Rullial multiway system.
Yeah, you look at, as I say, you take a Rullial multiway system, you look at a particular multiway system corresponding to a particular field of mathematics. The way that that's derived is by taking a collection of Rullial multiway branches and defining equivalences between them, right?
Yes.
And hence collapsing them down to single branches, the collection of which then produces a single multiway system. So then, in other words,
hold on. Actually, I just realized something else, which is kind of obvious, isn't it? That the full Rullial multiway system, there is only one full Rullial multiway system.
Up to quasi-conformal diffeomorphism.
Fine, up to relabeling, up to reparametrization.
It's not relabeling, it's a diffeomorphism. Right?
It's a reparametrization.
Each universal model of computation has an associated Rullial multiway system. The topology is invariant, but the geometry will change.
Right.
So anyway, so in other words, each multiway system can therefore be thought of as a fiber in the overall Rullial multiway system. And so the process of performing this collapsing is a fibration, just like the process of applying the univalence axiom in homotopy type theory is the fibration of a type space.
Okay, let me just walk through that slightly more slowly. I think I'm understanding. By the way, it was pointed out, somebody pointed out that this person, Andrzej Bauer, who's somebody I've known for a long time and have various useful interactions with, is a big expert on univalent type theory. And we should probably get him into one of our live streams. and I should probably, as soon as we're ready to talk about this, I think we should get Andras, because I think he would have useful things. But anyway, okay. So, okay. So then, a particular, well, you can call it, okay, a particular multi-way system is a fibration, you say, of this.
Is a fiber, right? The vibration of the Rulio multi-way system yields individual multi-way systems, and the vibration, just like the vibration of an individual multi-way system, yields individual causal graphs.
Right, is a fiber of this Rulio multi-way graph.
Right.
Okay, I agree.
Mm-hmm.
So what does that mean so what was the analogy with the univalence business?
Well, the way you derive that is through application of the univalence axiom. So, like I say, your full Rulio multi-way system is the free topos of mathematics. Right, it's all possible mathematics is.
Indeed, as it is also all possible descriptions of the physical world.
Right, which by Church-Turing are the same thing.
Except that what we're claiming is something beyond that, which we're saying that the physical world is all of those things, in a sense.
I mean, right. I'm also claiming that mathematics is all, well, okay. My basic claim is that the structure of mathematics and the structure of physics is actually quite generic. And has more to do with univalence and the structure of the Rulio multi-way system than otherwise you might suspect.
I agree with that. But the point that I'm trying to make is the very reduction. See, what I suspect is this, okay? Most of mathematics, just like most of physics, is irreducible.
Yeah, I know. I get that, right? I understand what you're saying. You're saying that by imposing the relations that correspond to particular axiomatic systems, you are taming a certain degree of irreducibility.
Exactly.
Yeah,
But by picking a particular, is it a particular class of fibers or what is it?
With picking a particular fiber, right? It's exactly like if you're trying to solve the word problem, you can pick.
I think it's more general than that. I think that this univalence axiom is not necessarily being specific about the fiber.
No, of course it's not. It's the thing that allows you to construct the fiber.
Okay, so what we're saying is that to reduce to a single fiber, as opposed to having to look at the whole multi-way system, we have got to get Rulio into the frigging spelling dictionary. I'm going to send another piece of mail about this. Maybe we have to wait until a new version, but I don't think so. I think it's backwards updatable. It's a new word. So that I don't find out that it gets rejected because it isn't in a dictionary yet. Okay, to reduce to a single fiber. Okay, what you're claiming is that there's an equivalence class. What are you claiming about this, about how you reduce to a single fiber?
I mean, like I say, nothing new. It's just that your particular choice of axiomatic system corresponds to a particular set of relations that you're imposing on the free topos.
I know, I understand that. Right. But where does the univalence axiom come in?
That's how you produce the fiber. It's how you collapse. So the set of equivalences then becomes a set of identities between branches, which therefore allows you to collapse this overall Rulio multi-way system down to a single multi-way system.
Let me just walk through that. So your claim is that in the Rulio space, the equivalences between branches in Rulio space are These are alternate multi-way systems, alternate axiom systems. See, that those are like each multi-way system is each rule-like separated. Okay, there are rule-like separated events, right?
Yeah.
And are you claiming that there is an equivalence relation that goes across rule-like separated events? Is that the equivalence relation you're talking about? The one
that's what axioms are.
No, axioms are defining a set of rules. No, I don't understand that. The axioms are not, I mean, you're saying a particular foliation, essentially, of the rule multi-way system corresponds to the application of a particular axiom system. Right?
Am I? Okay.
Well, I think, I don't know. I mean, that seems like a correct statement.
I agree, but I don't think that was the statement I was making.
Okay, so what was the statement you were making?
So an axiom system is a collection of relations on the free rulal topos. Right.
I'm going to write down that statement so that I can at least ponder it. Okay. Axiom system is a set of relations on the free rulal topos.
Right.
Okay, so the topos, just to remind myself, the topos, what is the translation of the topos to our world?
So the free topos is just the rulal system with no relations applied.
Okay, right. Free topos is rulal is the analog of the free group. Basically, it's what is the definition of a topos relative to a group? I mean, it just doesn't have any of those relations, right? It's just a free. Okay.
Well, it's unlike a group, the morphisms don't have to be isomorphisms, and it necessarily possesses a concept of categorical localization.
Okay. So the free topos is the full rulal multi-way system. Okay. Then what?
Right. So then an axiom system is a set of relations that are imposed on the free topos. Right?
Yes, I agree.
So each axiom is defining an equivalence relation between branches of the free rulal topos.
Yeah, I agree.
Right. And so then the univalence axiom is what allows you then to say that the branches that are equivalent under that relation can therefore be merged, and therefore allows you to construct a fibration for which that axiom system is a single fiber.
I'm a little confused by this because I think there are two different ways in which these relations are getting used, and I'm a little confused by that. One is, oh boy. What is the relationship between the univalence axiom and foundational axioms of set theory? In other words, is the univalence axiom basically, what is the core thing that one is assuming in order to do mathematics? I suspect it's some statement that proofs. It's some statement that a proof has just a true-false result somehow. In other words, that mathematics is about results, not showing your work, in some sense.
Okay.
I mean, in other words, the point is that mathematics, as it is practiced, is simplifying. It's the same. It has to be ultimately philosophically the same thing as what we're doing in the physical world. We are simplifying all of the little complicated things that are going on in the little rewrites of the hypergraph. We're simplifying those things in what we choose to see in the world. And what I think has to be the case is that similarly in mathematics, you're simplifying, it's like if you were to have to show your work everywhere,
Yeah.
then there would be no conclusions in mathematics.
Right, exactly. So it's the univalence axiom. That was why I was making the statement, before, that the univalence axiom is the essence of quantum mechanics as well. Right. Your statement that we don't care about the individual microscopic updates of the hypergraph is the completion interpretation. It's the thing that defines the equivalence relation on microstates. Right.
Yeah, something like that, right.
So then the univalence axiom is the justification then for saying if those microstates are observationally indistinguishable, then they can be treated as a single state. They can be merged in the multi-way system, which is the statement of univalence.
Yeah, I understand. I think that's also the same statement, isn't it, as the equivalence. What is the analog of the completion business in the spatial case?
Coarse graining.
So the completion, so what you say, no, but wait a second. But what forces causal invariance? So you're saying even if the underlying rules aren't causal invariant, you still get relativistic invariance because there is a completion being done by the observer. And what is that completion? That completion is some form of coarse graining.
Yeah, right.
Is it obvious exactly what? I mean, in other words, the spatial coarse graining, I think it probably is somewhat obvious. It probably has to do with little light cones and things. That if you are somehow conflating things within a small light cone, that is that obvious? That is like a completion?
Well, my position on it is the same as the one I had sort of a year ago, right? That it's just that the events are small compared to the size of the observer. That's all that's happening.
For what? For the spatial case?
Well, for the standard quantum mechanical case.
No, I understand. But what I'm asking is there a direct analog of that in the spatial case?
Yeah, ordinary statistical mechanical, coarse graining.
Well, it will be interesting to prove that analogy because that's an analogy. Why?
Because they're just Wick rotations of each other. Swap the spatial and branchial coordinate axes, and it's the same procedure.
Yes, but it's not obvious that in the spatial case that it corresponds to localized spatial things, is it?
Ooh.
Right? I mean, it's not obvious that a completion. Your basic statement is it is localized. Yeah, actually, that is obvious, right? It is obvious because those are. It is obvious because the completions are just the opposite sides of little light cones.
Yeah.
As opposed to the opposite sides of little entanglement cones.
Right. Right. An elementary branch pair in the spatial case is an elementary light cone.
I think I hadn't really internalized this properly before. So the basic point is a completion is the crushing of, a completion is the crushing, or is the squashing to zero of an elementary entanglement cone or an elementary light cone. I mean, the thing that's remarkable about this, okay, is that what this is basically saying is the fact that the observer lives in the same space as the underlying system implies that causal invariance is irrelevant. I mean,
Yes.
implies that underlying causal invariance is irrelevant because you will always get effective causal invariance as a result of this completion process.
Right. Right.
And then you're saying that the fact that the completion process is doable, you claim, is equivalent to the univalence axiom.
Yes. In particular, if one considers the generalized Wick rotation, right? So instead of swapping between spatial and branchial coordinate axes, but you swap between branchial and rulal coordinate axes, then quantum mechanics just becomes the operation of an automated theorem prover.
Okay. The fact that the completion is possible is a consequence of univalence. You know, I hate this name univalence. I hate it. I don't understand it, and I hate it. We really should figure out a better name. Why is it a good name? Or would you not argue that it's a good name?
I don't have a strong view.
Okay, so Wick rotation in rulal space is the completion is a crushing of a elementary basically of a rulal elementary cone.
Right, or a critical pair.
Well, they're all these things are critical pairs.
Right, but crucially a critical pair in the standard sort of theorem prover sense. Right, like I say,
yes.
the action of quantum mechanics in branchial space becomes exactly the operation of an automated theorem prover, of a general automated theorem.
Well, you mean the operation as in what you're saying is the observation. No, look, observation in quantum mechanics is like theorem proving in mathematics, is what you're saying.
That's what I was saying.
Right, but so let's just understand that analogy more closely. So the point about theorem proving is what theorem proving does is it conflates things. What theorem proving conflates equivalent things. Theorem proving, you know, it conflates equivalent expressions basically with effort, so to speak. Whereas observation in quantum mechanics is conflating equivalent states. So again, the statement is that the fact that theorem proving, what is the point of the axiom? The axiom is saying, what on earth is the meaning of this axiom? I mean, that is, it's saying it is reason that we humans, when we are choosing the mathematics that we do, choose mathematics that has this feature that it observes the rulal space in this way. That's basically what we're saying, right?
Is it?
I think so. Right, so the point is, again, okay, the physics that we're doing is observing rulal space, branchial space, whatever, in a certain way. We are picking out only certain features. Call it coarse graining, call it whatever you want to call it.
Right, no, yeah. That's we already knew that, right? That everything is just a time-ordered sequence of equivalence classes between states. Right. What the univalence axiom is saying is it's giving a formal justification for the completion procedure, for saying that from equivalence we can deduce identity, and that deduction is itself an equivalence and therefore can be represented by rules.
No, I don't think that's philosophically right. I mean, that's formally correct, but the philosophy of it is, the univalence axiom is a choice about how we choose to extract our mathematics out of this Rulio multi-way system, I think. That is, the univalence axiom does not need to be there. It is there because that is part of our human process for reeling out mathematics out of the Rulio multi-way system, I think.
But it's also what gives us quantum mechanics. And
well, it's what gives us
mechanics.
no. I know it's what gives us no. But again, my claim is these are all choices, right? I mean, you're correct that it is the same. It is a choice. It is a reflected back on us humans choice about how we choose to understand the physical world and the mathematical world.
Yeah.
Right? I mean, it's important to realize it's a choice because it isn't self-evident. It is a trick, basically, for extracting a slice of reducibility out of what would otherwise be a messy, irreducible situation, I claim.
Yeah. Oh, yeah. Oh, yeah, right. But what's the...
Okay, my point is this, that it is super interesting.
Know that humans are computationally bounded, right? So in particular, their input data rate is higher than their level of computational, their level of processing power, and therefore they have to construct foliations.
Indeed.
So the univalence axiom is an inevitable consequence of the fact that humans are computationally bounded agents.
Well, it's not the only conceivable thing you could do. It is the thing that we think of doing.
Well, you need to have a way of constructing an identity relation.
Well, in just the same way as you have to have a way of constructing integers. I mean, I don't think it's self-evident.
No. Much deeper way than that. You can't process the whole. That's the whole point, right? You can't process the Rulio multi-way system because you're a computationally bounded agent. So you need to have some identity relation, so you don't have to process the whole thing. And the univalence axiom is the statement that the natural way of doing that is by conflating the identity relation with the observational equivalence relation.
I completely agree.
Which, when you think about it, is actually the only identity relation that you could have constructed anyway, I think.
That's what I'm not so sure about. I'm not so sure about that.
What would be another one?
I don't know. I have I just have human imagination, so to speak. Right? I mean, yes, it's the idea that you conflate, the idea that you take an elementary light cone or something like it and squash it to a point seems like an obvious thing to do, right? But I can't tell you that that's the only possible thing you can do. I mean, I think that it's not totally clear to me that that's the only thing you could do.
But I'd say you have to do at least that.
Yeah. Okay. Well, I mean, yes, it is. Look, all these statements are the same. The fact that we need slices of computational reducibility. The question is this the only way of slicing out computational reducibility? You claim it is the only generic way to slice out computational reducibility. It is the most generic way to slice out computational reducibility. That's I think your basic claim.
I'd say so. Yeah. Or it's the minimal generic way of doing it.
Right.
My point is, if states are observationally indistinguishable, if they're observationally equivalent, you cannot help but conflate them.
No, I understand. Observational equivalence, assuming, oh boy, I am holding back on whether I agree that this is inevitable. I think this is as inevitable as, everything that has been invented, that could be invented has already been invented type thing. It's not obvious to me it's the only way to do it. And it seems hard to even imagine a proof that it's the only way to do it. I mean, okay, doesn't matter. I mean, this is it's already. Listen, we don't necessarily have to solve the problem of science for all possible aliens. Let's be content for now, just solving the problem of science for humans.
Right.
The human market is the only known market at this time, ignoring the creatures of light and other such characters who may be flitting around. But what is the relationship? See, what I think is really interesting is this point that, okay, when people invented set theory, okay, what is the relationship? What's the point of contact between the univalence axioms and set theory? In other words, do the univalence axioms imply a whole bucket of set theory axioms?
No.
Okay. In what sense? I'm sure that this property of observational equivalence is the same as identity is also captured somehow in set theory.
Yeah.
How? How is it captured?
I mean, isn't this the axiom of equivalence? I forget what it's called. Hang on.
Like sets which have the same elements of the same set or something?
Right. Is that axiom of identity? I never remember the ZFC names.
I don't know them. I don't know them at all. Let's look them up.
Yeah, axiom of extensionality.
Okay. What does it actually say?
Yeah, two sets are equal if they have the same elements.
Okay. And that's the thing then that allows you, presumably that is the same statement as this univalence. That's the core statement that the univalence axiom is also making.
Something like that, yeah. But like I say, I think the univalence axiom, everything we've discussed so far is only dealing with the superficial case of the univalence axiom. It's saying something much deeper than anything we've discussed here.
In what sense?
Because it's not just saying that the equivalence implies identity. It's saying that equivalence implies identity, and that implication is itself an equivalence relation. And that's the thing that justifies completions. Right? That's the thing that I think is exciting.
That equivalence relation between what and what? I'm sorry.
So A equivalent to B is equivalent to A identical to B. Right?
Yes, I know that's the univalence axiom.
And
yes.
but that equivalence thing in the middle is itself an equivalence type.
Yes.
Right. So what that's saying is, if A and B are observationally equivalent, then we can treat them as being identical. That's the superficial level. But much more importantly, what it's saying is, because that relation is itself an equivalence relation, we can enforce that identity type as a rule in itself.
I see. And that is the completion, is what you're saying.
Right.
I see. So the basic point is the univalence axiom.
Right. And I mean, and that's why it's called univalence, because it's saying there is only one type of equivalence.
I see. So univalence axiom. Okay. So the claim is that, okay, it claims to say there is only one type of equivalence, and let me understand this again. So, oh gosh, walk me through this again. I already lost it. So the thing, it basically says the thing it says is A equivalent to B is equivalent to A is equal to B, right?
Yeah. Right.
Okay, now walk me through then. It's equivalent to, so that middle equivalence, you say, is the completion.
Right.
So that's saying, so wait a minute, the middle equivalence is a completion. So you can then apply the axiom again to that equivalence.
Right.
So then, so what? So wait a minute, so what does that do? What does that do? That means that
It gives you a way of enacting it. It means that you can represent you can enforce the equivalence relation by adding rules.
I see. You can implement the equivalence relation So let me understand that. So that's saying that what the hell does that mean? So okay, so why is that important? Okay, what's the philosophical importance of that statement? So it's saying that by letting the observer, that the observer is like a piece of physics or something. What is the philosophical significance of that claim?
Yeah, I mean, something like that, right? It's saying that your vibrations of the rulal topos can be constructed just by adding additional rules. And that immediately implies all the stuff we already knew about quantum mechanics and statmech. And
yeah, but what does it mean that you can get there just by adding rules?
it means that you don't need miracles. You just need the operation of the rulal multiway system.
Because those rules are somewhere in the rulal multiway system. Is that your claim?
I guess you could think about it like that, right? That a bit like with generational multiway systems, they're rules that you would have got to anyway if you gave it enough time. You're just kind of speeding up the process.
Right, but that's saying, I mean, the observer in quantum mechanics. See, the question is, what's the observer in mathematics? That's the question.
Why is that a question?
Because I think that's the whole point is, that's the thing. The observer in mathematics is a computationally bounded observer.
Yeah, of course, right. Just like in all other frames. So, which is
right,
why the axiom system defines a set of relations, just as it does in quantum mechanics.
I know, but the statement that the observer in mathematics is computationally bounded, I think, has a sort of profound implication for the philosophy of mathematics.
I don't think it explains why we need axioms.
Well, it explains the slicing, the thing which, the is mathematics invented or discovered type thing. It explains the slicing of mathematics by
axiom systems.
No, but it's more than that, because it's more than that.
Why?
It's explaining. No, it's explaining a feature of axiom systems that we choose to use. Because I claim there are plenty of axiom systems, I've even enumerated some of them, that are really useless to us.
Yeah, because they enact very trivial reductions of the rulal topos.
Well, in other words, they don't cut deep enough in terms of making things equivalent, is
right.
what you're saying.
You want your fiber to be thick enough that it has richness, but not so thin. It's thick enough that it has richness and isn't totally trivial, but not so thick that it's computationally irreducible, right?
Well, I know that. Yeah, right. I mean that, but that's this we already know. I think it's getting late for you, and I'm sorry. You always get more. You get you imply more stupidity on my part the more tired you get.
Sorry, that's a
it's okay.
limitation of my.
You get no. I can put that differently. You get more impatient the more tired you get, which is there's a little bit more to this. Okay, the point is the mathematics that we do is computationally bounded mathematics.
Mm-hmm.
The fact that it is possible to do meaningful computationally bounded mathematics is somehow connected to the fact that there's something about mathematics, about the definition of mathematics, that goes beyond just the throw a random axiom system in there. And I think it's something to do with this don't bother to show your work property.
Which is a causal invariance property. I mean, that was the point. I mean, that's the thing I kind of wanted to get to, right? Is that I think what we figured out here explains why mathematics has the structure that it does. And it's a consequence of the combination of univalence and causal invariance.
So let's understand that for a second.
I mean, because the thing you were saying about not showing your work is the statement of causal invariance.
Exactly, yes. Causal invariance
right.
is equivalent to you don't need to show your work. Okay. But okay, so that's but then what's the role of univalence?
That's how you get there.
Okay, but what would mathematics look like if you always showed your work?
Well, the rule topos.
Hold on. Look, here's the point. I think, okay, the lack of undecidability, the unrifeness of undecidability in practical mathematics
is the same thing that allows quantum measurement.
Let's walk through that claim.
The
halting, that there are non-halting, there are trivially halting computations.
So the point is that the Rullial spaces topology is governed by computability theory, right? So in particular, from the topology, we can determine what's decidable and what's undecidable. And so being able to apply the univalence axiom involves making certain assumptions about the topology.
Yes.
Because you're basically, you're not allowed to apply unifications to things that exist on either side of a Rullial event horizon. And that's the same thing that allows you to make measurements in quantum mechanics. You have to make certain assumptions about the topology of branch yield space in order to make, in order to be able to make measurements in quantum mechanics.
Well, yes, it is it is this crush the entanglement cone to nothing. And you can't do that if the topology is too funky.
Right, yeah, if the two sides of the entanglement cone lie on either side of an event horizon.
So the claim is the ability to make measurements is an ability to crush cones, basically.
Right.
Okay. So in mathematics, what cone are you crushing? You're basically crushing the cone. In mathematics, that's saying you don't want too much undecidability. In mathematics, equivalences must be decidable. Just like you're saying that there are decidable equivalent. There are useful decidable equivalences, which is to say, it could be the case. That's not even right. Look, it could be the case in physical space or in branchial space that the crushing of the entanglement cones cannot be done systematically.
Yeah, if the topology is too hygienous. So the ability to apply the univalence axiom as a consequence of the underlying topology. That's the point I was making. So the crushing of cones in mathematics is the resolution of critical pairs in an automated theorem proving system. The crushing of cones in branchial spaces, quantum measurement.
Okay, but so the crushing of cones by systematic means requires not too much wildness in the topology.
Mm-hmm.
Because one of the things we're doing is the observer, crucial point, the same observer can observe many things. The observer doesn't have to be custom built. The observer is universal.
Uh-huh.
That's actually a relevant point. There is a possibility of a universal observer. And that might not be the case. So the concept of a universal observer, and that's probably the fact that there can be a universal observer in mathematics is they can be universal when the univalence axiom applies. I think.
Right.
In other words, it's not self-evident that there can be a universal observer who can untangle, who can crush cones everywhere.
Right, because because one observer could be trapped behind an event horizon that another observer doesn't see.
Right.
So in order to be able to apply the univalence axiom, you have to make certain assumptions about the topology of the radial space.
Right. So what was I going to say here? An observer.
It's like how if you have an event horizon in ordinary physics, you can't have a universal observer.
Right. Well, so one way to think about, okay, so the topology can't be too wild. E.g., there can't be an event horizon.
Mm-hmm.
Otherwise, you can't complete across that event horizon.
Right.
But the possibility of a universal observer in mathematics. Yeah, here's the point. Okay, it is not self-evident that we, an observer of a certain type, can go everywhere in the universe and still make sense of it.
Right.
It's not self-evident, but it appears to be true. Mm-hmm. Okay, in mathematics, what is the analog of the existence of a universal observer?
The intersimulability of axiom systems.
Which is truly a mess. I mean, those are hardly okay, but look,
is it?
Of all, I mean, I've tried to do it. In various cases, it's really non-trivial.
No, but at least theoretically, it's straightforward.
Yeah, theoretically, it's straightforward.
Right.
But the big mystery.
They're mostly all universal.
Right. The big mystery of mathematics is why it works, right? Why we can do mathematics as a bounded observer, why we can conclude anything useful in mathematics.
Right.
Which has to be the same reason that we can conclude useful things in physics.
Yes, right. This is why it's interesting. I mean, so the point is, quantum mechanics in physics is a consequence of the topology of branchial space that allows the application of completions, and relativity is a statement about the limiting geometry of the space that arises from causal invariance. And the point is that there are generalized versions of the same things. There's a consequence of the topology of Rullial space that permits the application of the univalence axiom, and there's a generalization of the Einstein equations that holds as a consequence of the resulting geometry.
And what is that?
Well, that's what we have to figure out.
What are JD6 in Rullial space?
Proofs.
Okay. Yeah, that's obvious.
But one of the things that I think is kind of interesting, well, I mean, so we know that whatever these generalized Einstein equations are, there's some kind of statement about computational complexity theory. Right? Because that is the induced geometry.
Yeah.
Or to put it more mathematically, it starting just from proof theory, i.e., from the combinatorial structure of the Rullial multi-way system, it's the thing that gives you the model theory.
Model theory is the geometrical analog of model theory is to proof theory as geometry is to topology.
So that's the non-trivial observation that I'm kind of being drawn to as a consequence of this.
Well, I know a big expert on model theory. Who would be happy to talk about this.
Okay. So the basic idea being, so if this is right, that so if you think about quantum mechanics is really a statement about topology, and relativity is a statement about resulting geometry, then you can say things, so then what we're really saying is this gives us what in category theory you would think of as a functorial map between algebra and analysis, because it's saying, like the structure of, say, the Rullial multi-way system, that's an algebraic structure. That's something you can describe syntactically. But then it has some resulting geometry that happens as a consequence of the univalence axiom and causal invariance and so on, that you can describe using analysis and geometry. And so again, it implies that computational complexity theory is the geometrization of computability theory. And so in each of these cases, what you have is the syntax as described through algebra on the one hand, and then the semantics as described through geometry on the other hand, which arises only after you apply univalence and get causal invariance and things like that. And so in the case of in the foundations of mathematics, the syntax is the proof theory and the semantics is the model theory. So it would imply that the geometrization of the Rullial multi-way system as viewed in terms of mathematics should give you model theory.
Walk me through why model theory is geometrical. I mean, so proof theory is there exists a path from here to there.
Yeah.
So
right.
A model of a particular axiom system should be thought of how? As
a foliation. Right. So this is what I think is kind of amusing, right? That it gives you, okay, so what does Gödel's first incompleteness theorem really say? What it really says is that there's gauge dependence in mathematics.
Let me understand that statement. Okay, first of all, why is model theory a foliation of the proof? Okay,
because of the gauge dependence.
Okay, so the claim is that model theory is a foliation of the proof multi-way system.
Right.
Okay, let me just understand that claim. Let me just remind myself what model theory is in that context. So model theory is an interpretation of what the operators mean, so to speak.
Right. It's Given a set of axioms, it's giving you your domain of discourse of a set of objects that are consistent with those axioms.
Okay, so we have this collection of this multi-way system, and then the question is what? Let's see. Have that multi-way system, and so now, as we foliate the multi-way system, we're saying, at this step in these proofs, I'm not quite getting this yet. I mean,
yeah. So like I say, it starts with this realization that Gödel's first incompleteness theorem is a statement of gauge dependence, right?
I don't understand that claim. What do you mean by that claim?
Well, so the first incompleteness theorem says that in any axiomatic system that's capable of simulating Peano arithmetic,
yep,
there will be models. There will exist statements in which there exist models where that statement is true and models where that statement is false. Right?
Yes.
So in other words, there is arbitrarity in your choice of models. So one interpretation of the first incompleteness theorem is, given a set of axioms, given a proof theoretic framework that is at least as rich as Peano arithmetic, there is an infinite redundancy in the models that you pick.
All right, but I'm trying to understand the difference. So like for example, in my random pictures of in my typical, like, these pictures of, here are a bunch of proofs, right?
Yeah.
I know I discussed this here. What's the relationship between models and, well, let's take a look here. So given this type of thing, the significance of a model here is that it basically takes one of these statements and basically turns it into, you could think of it as turning it into a number, turning it into something concrete for which these things become self-evident. Does that make sense? I mean, in other words, given a model for what that operator is, right? These things become trivially true or not true. I'm trying to understand the relationship between the model and these paths. I mean, what is a model in Rulial space? What is a model?
Well, I mean, that's what I'm getting to, but I need to make sure that we're on the same page about what we're discussing here, right? So obviously in these pictures, as you well know, your P and your Q here are being quantified over.
Yes.
So your model is an explicit declaration of the domain of discourse, of the set over which they're being quantified.
You can think of it that way, yes.
Right, okay. So like I say, so then Gödel's first incompleteness theorem is a statement of coordinate redundancy in the proof multi-way system. So in particular, therefore, it means that a particular choice of model is a particular choice of coordinatization, and therefore is geometrized.
Hold on. So, I mean, why is this? I mean, I understand the words you're saying, but I'm trying to understand what the. So we have one of these multi-way systems here.
Yep.
And you're saying.
But this is just an ordinary multi-way system.
As opposed to what?
As opposed to a multi-way system of all possible proofs.
No, this is all possible proofs. You can these paths correspond to the possible proofs for this particular system. So I don't disagree that I think you might very well be right that the model theory of this is to coordinatize these states.
Okay, but if these are proper proof for multi-way systems, then yes, that's definitely true.
Well, proper what?
If they are proper proof multi-way systems, if they are in fact proof multi-way systems.
What do you mean? I mean, they're just multi-way systems with certain rules. What do you mean by a proof multi-way system?
That they, yeah, okay, fine, yes, yes, we're okay.
Okay, so then the question of model theory. So you're going to make a statement, which, if true, is very interesting. That model theory coordinatizes Okay, does model theory coordinatize statements? Because that's, I think, what you're saying is that,
Yep.
because that's, I mean,
Exactly.
okay, so claim model theory. So in other words, once it does that, then it is obvious that different models correspond to different foliations. If that's true, that
Yep.
model theory coordinatizes statements.
Right. Which is
Can
the
you,
which. Yep.
can you walk me through why you think that's true? That it seems about right, because it seems like what you're doing is you're saying for any given statement.
Well, yeah, it's a gauge choice because, like I say, because the first incompleteness theorem is a statement of gauge independence.
No, but look, if I have something that says f of a, b, c, whatever it is, I'm assigning a specific, I'm assigning specific values to a, b, and c, and to f, and so on.
Yeah, I know.
Right. So I could actually derive, if I wanted to, I can actually derive a value. I mean, I can derive some set of, I can like machine learn. I mean, it's like an encoding function in machine learning or something. I can take this thing and I can grind it up into numbers. But for that, well, that's actually a bad analogy. But I mean, basically, the analogy there would be the I'm still, just a second. Let me think about this for a second. You're saying
which part of my argument is the problematic one?
I'm trying to wrap my head around the intuition that model theory coordinatizes statements.
So I'm saying that are you disagreeing that model theory is a gauge choice, or are you disagreeing with the interpretation?
I don't understand that statement. I mean, given this statement, that model theory coordinators as statements, then I agree that model theory is a gauge.
No. The gauge argument is the argument for why this statement has to be true.
Okay, so walk me through that argument then.
Okay, maybe it's better if we go back to the relativistic case, right? So, what is a foliation of a causal network, right? There is a gauge. The thing that allows you to construct foliations of a causal network is the fact that there are many possible space-like hypersurfaces that are consistent with the partial order.
Exactly.
Right. So the causal network is a purely combinatorial structure. It's not coordinatized. There's no geometry.
Yep.
But then you can coordinatize it by constructing space-like hypersurfaces, and there is redundancy. There is gauge redundancy because of the fact that there are many possible such foliations that are consistent with the causal partial order. So that we know that's true in relativity. My point is Gödel's first incompleteness theorem is the analogous statement for proof multiway systems. Right?
Why? I don't understand that.
Because the first incompleteness theorem says there exist independent statements. There exist statements that are independent of the axioms if your axiom system is sufficiently rich. Right?
Yes.
So what does it mean for a statement to be independent? Well, it means that there will exist models in which the statement is semantically true and models in which it's semantically false.
Mm-hmm.
So in other words, what it's saying is that there is there is redundancy. There is an infinite redundancy in the choice of models. In the same way as there are many possible choices of foliation
I get that argument.
network
that
are consistent with the causal partial order. There are many possible models that are consistent with the proof multiway system.
Exactly. Right. But the proof multiway system, the proof multiway system defines essentially a partial order on statements.
Yes.
Okay, now, to get a total order, the claim is that a total order corresponds to a specific model.
Right.
Okay, that's the part I don't yet get. I mean, I understand your argument for it, but there's got to be a very direct argument for that. And I think it is just, I think it's really pretty direct. I think it's basically just saying that given a statement, I mean, it seems intuitively correct, but I think there has to be a very, very clean way to understand this.
Okay. I thought this was a clean way of understanding it. Maybe I'm confused.
I think there's a really, really, really direct way. Just like,
How? Okay.
okay,
How is
the
this,
reason is, what's
I
that?
mean, how is this not direct?
Okay.
In ordinary relativity, you're saying there are, if I fix some event,
Yeah.
and there's another event that's space-like separated, what I'm saying is there will exist some foliations where the first event comes first, and there will exist other foliations where the second event comes first.
Yeah, but the comes first thing isn't quite the same as I mean, I understand that it is analogous to the Gödel thing, but it's not quite. Go ahead.
What do you mean? What do you mean it's not analogous? It's the comes first thing is can you prove A from B, or can you only prove A from B, or can you only prove B from A? So the first incompleteness theorem similarly is saying there will exist some models in which A is only deducible from B, and there will exist other models in which B is only deducible from A.
Right. Look, I'm sure this is correct. Okay. My claim is there is an unbelievably direct way to see this from string multi-way systems, but we don't yet know that. Right. I think there's an unbelievably direct way that is a way of coordinatizing, insofar as you can think about proofs in term rewriting systems. Okay. Forget Peano arithmetic, just consider a term rewriting system and ask the question, what is the analog of a model in a term rewriting system?
Mm-hmm.
Okay. I think if we get that, we will get something unbelievably direct here. That is, what you're basically saying is, in the term rewriting, what is the question? The question is when you foliate this thing, right, you're going to get a certain order of, what is simultaneity in proof theory?
Well, it doesn't exist in proof theory. It's a model theoretic concept.
Okay, whatever, in model theory. What is simultaneity in model theory? Simultaneity is, go ahead.
Equivalence.
Equivalence of models. No, a model.
No. Equivalence of states subject to that model. Equivalence of expression subject to that model.
Right, but the equivalence usually in one of these things, the proof we imagine, and this may be what's confusing me, the proof we imagine to be a set of equivalences.
Yes, right, but the model is defining more.
Okay, so these are like time-like evolution equivalences, and the model is defining additional equivalences. Mm-hmm. Oh, yes, you're right. You're right. So the basic point is,
because if you to use your natural number example or whatever, if you interpret the operator as being plus and you interpret A, B, and C as being natural numbers,
right,
there will be some configurations of operators which are equivalent modulo that model, but which are not which are inequivalent in the proof.
You're exactly right. Yeah, a model defines equivalences between statements.
Right.
And which you could get by concretifying an operator or whatever else you want to do.
Right. So therefore, it's really it's a coordinatization of it's a gauge choice for the proof network for the proof network, and hence a coordinatization.
Okay, so a model defines equivalences between statements, which means that a model that a proof post equivalence, right? What does the proof mean, sort of post equivalence? What is the temporal evolution after you've modded out by the equivalence defined by the model?
Mm-hmm. What?
No, I mean, what's the okay, all right, then the test of whether we know what we're talking about is what is time dilation in model theory.
Well, there exist some models where the proofs are longer.
Okay, what's an inertial frame?
Well, some kind of canonical model that is kind of optimally suited to the axiomatic theory. But I'm not sure if is there a concept in that.
There may be, yes.
Let's see.
Well, wait a minute. Time dilation is that different models give proofs of different lengths. Is that right? That's not right. That will be the analog of different frames, right? That's not quite right.
Why not?
I see. Different numbers of slices of the proofial foliation, so to speak.
Right.
Okay.
I mean, yeah, the argument would be if you want to prove some statement about, I don't know, you could imagine that there are number theoretic statements that are much harder to prove if you just use natural numbers versus if you use rational numbers.
Yes.
For instance.
Yeah, some things are easier to prove over the reals. Well, your example is probably reasonable, over the rationals than over the integers. Okay. So then, what is this saying? So then the analog of an inertial frame. I mean, we don't really have an analog of an inertial frame in quantum mechanics, so.
No. I mean, well, as we've discovered, even defining inertial frames in relativity is not straightforward.
But we do have Zeno's paradox in quantum mechanics.
Mm-hmm.
So what's the analog of Zeno's paradox here?
Yeah, some kind of, well, there must be a speed-up theorem. If not Gödel's speed-up theorem, some related thing that is the analog, right?
Wait a minute. What do you mean? The speed-up theorem would be.
So obviously, the speed-up theorem is a proof theoretic statement. What we want is a model theoretic speed-up theorem.
What is which speed-up theorem are you talking about? The Blum, the manual.
The Gödel one.
Which is what?
Which is that if you have a you can shorten the length of the shortest proof by working in a stronger axiomatic system.
I see. I see.
The proof of which is incredible. It's it's a direct extension of the first incompleteness theorem proof, where he just constructs a statement that says this statement is not provable in fewer than n symbols for some value of n.
That's cute.
And then, yeah. Okay, let's see. Is there an analog of this in model theory? Yeah, this is where my poor knowledge of model theory bites me.
Yeah, well, your knowledge is probably better than my knowledge. But this friend of mine, Mary Anthea, is like a leading light in modern model theory, and she's actually quite philosophically oriented, and I think would quite possibly be able to answer this question easily. I can try sending a mail, although it's probably not a really easily described issue in mail.
This is Maliaris.
Yeah.
Right. Yeah. Cool.
Okay, so the question here. Oh boy, I'm just trying to think. What are the other? Okay, well, what we really want is Einstein's equations.
Mm-hmm.
And what we really want, the GD6 are proofs.
Mm-hmm.
The coordination of model theory. What is energy? What the heck is a causal edge? What's the significance of causal edges in proof theory?
Well, they're dependencies on earlier results. They're lemmas.
Okay. That's right. They are okay. They are they lemmas?
Well, they're things that feed into lemmas. I mean, so in fine equational proof, they're the things we would denote. The things we denote with dashed lines are really like causal edges.
Oh, this is so crazy. This is so freaking crazy. This is, I mean, the degree of unification is absurd.
Right, because I mean, if you recall, in a proof network, right, you have the solid lines that say we're using this result as our input, but then you have dashed lines that are saying we're using this other result from which to derive the rule that we apply to this.
Let's just look at an example of that. Okay.
Yeah.
That was a very trivial one. Is that enough to see it? Let's get a more complicated one.
Yeah. Okay. that is enough, but probably not.
How do we get? Is this one a good one? Let's do.
It's a little bit better, but
well, let's get a real one then. Okay. You happy with this one?
Sure.
That's got full of dashed lines. I see almost no solid lines there.
Right. So what you should see is that, so between every pair of lemmas, there is a solid line and there'll be a dashed, and there's exactly one solid line, but there will also be dashed lines that come from other places. So what the solid line there is saying is, you take substitution lemma 26, you apply some rule to it, and you get whatever's below, presumably substitution lemma 27.
Mm-hmm.
Right. But then there's also a dashed line that leads into it. And what the dashed line is saying is the rule that we applied in order to get from lemma 26 to lemma 27 comes from this other lemma that we proved along the way. So in particular, what it's saying is we can't have proved that thing if we hadn't previously proved this other thing. So it's a causal edge.
Okay, so these are the lemma dependency edges, or the analog of causal edges.
Right.
Okay, so what's energy? It's a flux of lemma dependency edges.
Right, through a
model. Okay, we got to be able to do this. There's got to be a way to understand that.
Right. I mean, it's some kind of proof complexity measure, but
hold on. We can do this. We can do this. The flux of lemma dependency edges through, it's not through a model. The model is,
well, yeah, the model is the foliation.
Is the foliation. So it's a flux
through a part of a model, you know, through a
no, it's a model. It's not a part of a model. It's an equivalence class of expressions which are equivalent under that model.
right.
So it's the flux through that collection of model equivalent under the model expressions.
Mm-hmm.
Okay, so that means what the hell is that?
So is it abstraction? Because the higher the flux through that hypersurface, the more dependent that result is on previous lemmas, right?
Yes.
So in effect, what you're saying is the taller the tower of abstraction you have to build in order to reach that result.
That would be absurd. If that turns out to be right, that is just absolutely, totally absurd. Well, that's a very interesting potential claim. Okay, so then claim, possible claim, energy okay, so the claim here is that energy is the amount of use of previous results that you have to make.
Right.
AKA the height of the abstraction tower.
Right. So it's, you know, a trivial proof that just kind of goes sequentially would have very low flux of causal edges. Whereas a proof that involves building up a large amount of technical machinery would involve a very high flux. So presumably, yeah. So the first would correspond to a field like combinatorics, and the second would correspond to a field like algebraic number theory or something.
Right. So okay, so hold on. So if that's right, if energy is the analog of abstraction,
then the Einstein equations are a statement that the higher the amount of abstraction, the more critical pairs you get.
or, well, what does
the
it
harder
imply
it is
for
to
geodesics? It implies for geodesics that the presence of the higher the amount of abstraction is a deflection of geodesics.
Which is a critical pair, right?
Yeah, I understand.
Each critical pair is a microscopic deflection of geodesics, is a microscopic amount of curvature.
Sure.
So the critical pairs are a measure of how difficult it is to prove something. So the Einstein equations would basically just be the statement that the more abstract the field is, the harder it is
to prove things.
Yeah. The ultimate mathematical statement.
Okay, hold on. So the basic statement is the higher the amount of abstraction, the more geodesics are deflected.
Right.
And therefore, and so are longer. So the more abstraction there is, the longer the proofs are.
Right.
Now, is it the longer the proofs are? It is the longer the proofs are. In order to get from A to B, is that right? In order to get from A to B, you are deflected. Is the deflection the length of the proof? Does that give you the length of the proof, or is it
Well,
something different?
it's related, right? Because so the deflection, okay, so here's my picture of it. So the critical pairs are giving you the elementary holonomies, right?
Mm-hmm.
So they're in effect the thing that give you the R mu nu. The lengths of the proofs are given by the G mu nu, the little G mu nu,
Yeah.
and the abstraction is given by the T mu nu.
Sure.
So they're all related, but it's not.
Oh, but wait a minute. You know, the sun, for example, you know, a massive object,
Yeah.
right, sitting there is a piece of abstraction that is a necessary piece of abstraction. And given the existence of that abstraction, the proofs have to kind of, you know, what is the force of gravity?
Right. So it's saying if you any proof that kind of goes near that lump of abstraction is necessarily going to be longer as a consequence of veering towards it.
Right. So any proof that gravity in mathematics.
It's like you've got this trade-off, right? Of you can construct a longer, more circuitous proof that avoids that lump of abstraction entirely, but you know your trade-off is you get a longer proof, or you could kind of go the more direct route, but you're going to get deflected by this lump of abstraction, and then you're going to have to deal with that.
Well, okay, so gravity in mathematics is that proofs become longer as a result of the presence of abstraction. You know, I think we just solved the, you know, one of my other kind of, you know, I've been thinking about this what is abstraction question for ages.
Mm-hmm. Right.
That is the most frigging weird thing. I mean, that there's a definition of abstraction where abstraction is equivalent to energy. That's just crazy. But I think it's right. So let's just walk through this again. So abstraction is proportional to the density of causal edges. That is dependency. You know, there are more dependencies on, there's a higher tower of abstraction, means more of these causal edges, more energy. In the presence of that, it means, so let's walk through this again, that a proof that attempts to go near this part of statement space,
mm-hmm.
If you go near a part of a statement space that has a lot of abstraction, and then I'm going to ask an obvious question for just a minute. A part of statement space that involves lots of abstraction, then your proof path, okay, your proof path is supposed to be attracted to, isn't it? Your proof path is going to be attracted into that place where there's lots of abstraction.
Right.
Why is that? Why does that work that way? What does it mean that you're attracted in towards the abstraction?
Well, it means that you get more holonomy.
Yeah, that's right. You get
there are more critical pairs.
Is attracted to the region of abstraction because it's basically a freeway. Because one way to look at it, because all those causal edges give you a freeway in statement space, I think.
Something like that, yeah.
Okay, my almost parting shot. Okay, so what's a black hole? Did I lose you here?
No. I mean,
what's a black hole in this?
Isn't it just a?
It's a
decidable proposition.
Well, it's what we would think based on the reducibility idea.
Yeah, because it's like if your proof just stops, you get a proof-like singularity, or whatever we're going to call it. Those are the statements that can be proved in finite time.
Right. So, I mean, singularities. It's actually not a proof-like singularity, it's a model-like. The analog of a space-like singularity is a model-like singularity.
Right.
Yeah, as a statement that can be proved, as a decidable statement that can be proved in finite time. Well, I mean, honestly, a lot of these things. So the question is all existing mathematics just headed into a black hole? Is the only mathematics that people actually do that works associated with black holes?
Right.
It's probably very late for you. I mean, this is a very good result. This is very interesting. I mean, this is insane. What's the analog of the, I mean, yeah, there's things like the cosmic censorship hypothesis and so on, which we could look at.
I mean, I guess that's the statement that propositions that are provable in finite, decidable propositions that are provable in finite time will be associated with non-convergent critical pairs.
Yeah. But the question is, I mean, so what would this theory, okay, so this implies a concrete theory of abstraction. It implies a way to measure abstraction. And it implies an analog of the gravitational constant. Right? What is the analog of the gravitational constant?
What do you mean exactly?
Well, capital G is a thing that relates. What are the units of T mu nu here? The units of T mu nu are
you want to know how critical pair density relates to abstraction density?
Yes.
Yeah.
I want to know how the deflection of geodesics relates to abstraction density, which means we have to be able to give units for abstraction density.
Right.
And the units for abstraction density will be, let's see. So in the space-time case, the units of T mu nu well, T mu nu, what are the actual ordinary units of T mu nu? They're energy per volume, aren't they? Is that right? Energy per spatial volume.
Right.
So this is saying basically the analog of this is how much how many pass-through facts are there per number of statements? In other words, in the neighborhood of some statements, how much activity? Because the volume in statement space, we understand roughly there's a volume in statement space, and then there is let's see, where are we going here? So we're let's see. It's the number. It's the density of mathematical facts. Yes. Here's what it is. It's the density of useful, of independent and useful. Density of independent mathematical facts relative to the number of all combinatorially possible statements. In other words, if you just enumerate possible statements, by strings of symbols, okay, that's going to give you some volume in statement space. The question then is, of those statements,
what's the size of the volume when you mod out by the equivalence relations defined by the axiom system?
That's a way to say it. Or alternatively, with respect to this energy flux, it's kind of the density of useful facts out of all these possible combinatorially generated things. How many are independent? How many are independent and useful?
Right.
So it's the density. So in fact, I even have a picture of that in the NKS book. So that's T mu nu, is the fraction of T mu nu is related to the density of useful, of non-redundant, as well as used in proofs, non-redundant / useful statements. Okay. And proof length, so R mu nu is, I think, the extent to which the proof uses it's somehow the extent to which the proof uses non-trivial facts as opposed to just being a direct substitute type proof.
Right, the density of critical pairs, or the density of elementary holonomies.
What is an elementary holonomy in our discrete case?
A critical pair.
But normally a holonomy is a way, tell me what the definition of a holonomy is in ordinary mathematics.
The failure of geometrical information to be preserved under parallel transport.
Right. Well, okay. Well, anyway, so this is the gravitational constant is some kind of conversion. Proof deflection is in units of I don't quite know.
Well, critical pairs per unit volume.
Yeah, I understand. But oh, you think it's the same volume, right? It's the notion, the volume in statement space.
Right.
So you say it is, I see, it's the branchings and the proof.
Yeah, the critical
Right.
pairs.
Branchings and the proof. I mean, my question is, what kind of a constant is the gravitational constant here? And I think it's a constant.
What does that mean?
Well, it means, so in the case of the thing I was calling rho, which I think I should call psi. I think I should rename it psi. Anyway, the maximum speed in Riehl space. Okay. We interpreted that as a physical constant, right?
Yeah.
It's the processing power of the universe. The question is, what the heck is this? And I think what it is, what kind of a constant is this? Is it like pi, for example? I don't think so. I think it's a constant that somehow is at its core a condensation of kind of the condensation of kind of the representation of human knowledge, I think.
Right. It's a measure of the trade-off between computational effort and abstraction.
An interesting claim. Okay, so represents I see. So your claim is that therefore it is a, okay, but what units does that have? Computational effort is number of steps in a proof. Abstraction we're defining here
as causal edges.
Yeah.
Right, but the volume terms cancel, probably.
Yeah, I think so.
So it's just causal edge density per critical pair, which we can measure.
What do you mean you can measure? You mean in Boolean algebra or something?
Well, if you just take that proof graph, you can look at all the critical pairs, and you can look for each critical pair, what's the average number of causal edges. We can get empirical data for this constant.
For human mathematics.
Right. It'd be interesting to see what the diversity is like between different axiomatic theories.
The hell is this thing? I mean, so in other words, it's, whereas the other thing is a statement about the physical world, this is, yeah. Well, anyway, it's getting really late for you. I'm sorry, I should not keep you up. But
that's okay.
Just because we figured out the meta theory of abstraction, which I've been circling around for the last few years, in 5 minutes.
And it does have the neat implication that just like quantum computers only work to the extent that branchial space is expanding. It's like mathematics only works, or mathematical physics only works as a shortcutting process for computational irreducibility to the extent that this space is expanding.
Why do you say that? Why do you say that? Wait a minute. Walk me through that again. So you're saying, yeah,
there's the expansion of this proof space corresponds to the fact that there's some inevitable amount of abstraction that occurs just as a consequence of progression of mathematics, right?
Yes. So wait a minute. The expansion. Okay. So the question is expansion of statement space.
Right. So then the point is that Why do why develop a field of mathematics at all, right? When you could just follow a single linear proof path every time you wanted to figure something out.
Yep.
The point is, mathematics allows you to shortcut that process because you can make use of previously derived results, i.e., you can make use of the abstraction tower.
Yes.
Right. So the point is, mathematics allows you to shortcut, allows you to perform, computationally reducible operations in science, only to the extent that you can build up such abstraction towers.
I understand.
Otherwise, you might as well have just traced out the explicit computation. So the mathematics is only effective as a means of describing the universe, in as much as the proof space is expanding.
Yeah, only effective insofar as it builds up a bolus of abstraction, i.e., that the statement universe is expanding.
Right. So the
otherwise, yeah, sorry. Otherwise, you might as well just follow a free space geodesic of computational, operations, so to speak,
right,
without any shortcutting.
Right. So Wigner's statement is really a statement that the cosmological constant is non-zero in proof space.
I think it's different from that. I think because his statement is about its application in physics.
Mm-hmm.
And it's not obvious that there's a connection between, the connection between this and physics relies on our whole tower.
Right. It allows on being able to fibrate this space.
For physics, it means it's a consequence of the fact that the same space is the space of physics.
Right. At least post vibration by a conscious observer.
Right. This is quite wonderful. I mean, it's great. It's okay. It doesn't help me in getting this blog post written because it's now gone off in a ascended into some completely different direction.
Right. By the way, I mean, sorry, related to this but not related to the blog post. After that alien intelligences discussion, I was thinking about your statement about someone asked a question about whether aliens would invent numbers.
Yes.
And you kind of said no, probably. I mean, there's no reason to think that they would, given how sort of human-centric the axiom systems for numbers seem to be. But I'm becoming increasingly convinced that might not actually be true, because basically numbers are an inevitable structural consequence of any formal axiomatic system in which you can construct a successor function, right?
Sure.
And by the Church encoding, we know that that's equivalent to any computational system in which you can perform a repeated function application.
Sure.
So really the question is, how common is it amongst alien computational systems to be able to do nest?
Sure. And the answer is, if you look at the NKS book, it occurs in many but not all these systems. For example, the tiling systems do not have that.
They don't have nesting. Okay.
No, because they don't. They just say, here's a set of constraints, go be happy.
Okay. And do you have data about, I forget, is there actual sort of numerical data on how common it is to be able to do repeated function application in computational systems? And I know it's a hard thing to enumerate, but
only by looking at chapters of the NKS book. I mean, in which case the conclusion would be about 1 in, well, we can just look here. So It's more or less true in all of these. Register machines is a bit funky because they have a program counter. So they're not quite as successory as you would think. Now, obviously, multi-way systems are a little bit funky in terms of successiveness. They don't have a completely ordinary successor function. And systems based on constraints just do not. So I reckon, if we sample the nearby stars, some fraction will have them, some fraction, might have them, some fraction might not. I would say that the anyway. All right, listen, what's that? The things we, so this is great progress, and I think things that we still need to talk about here. We still need to talk about higher order corrections, general relativity, and looking at this equation, to what extent is the following thing true? To what extent is the general statement just that in the vacuum, the volume of geodesic balls is conserved?
Well, it's conserved in the sense that it follows a conservation law. Yeah.
Well, if T mu nu is equal to 0, then isn't it the case that the derivation would imply that basically the geodesic volume has to be 0? Has to be, it has to have no change, so to speak.
Yeah.
Right, but that means that implies that's a simple way to state the all orders version of the Einstein equations then. But the question then is the interpretation of the conservation of geodesic ball volume. And the point is that the continuum limit of the geodesic ball volume has all, the measurable things, the locally measurable features of that are these derivatives of the Riemann tensor, as I understand it.
Yeah.
Is that cubic term relevant, by the way, or does it go away?
Which, sorry?
That cubic term there.
That probably disappears, I would suspect. I think you only expect even terms. Unless you have a torsion metric or something weird.
Yeah. But then these higher order terms, the question is the all orders statement that the volume of a geodesic ball is, like in the evaporation of a black hole, what does that mean?
I don't understand the question.
The question is, in the standard Einstein equations, right?
Yeah.
You can make various statements about the structure, like the Schwarzschild solution or something like this. Okay. If all you did was to say, just change the Einstein equations to not talk about pure R mu nu, blah, 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 but instead replace R mu nu, replace that whole piece by the volume of a geodesic ball, right? And simply ask, in the Schwarzschild solution, we want something where the volume of a geodesic ball doesn't change as you move around the space.
Which is just the vacuum Einstein equations.
But doesn't the volume of a geodesic ball, it has these higher order terms?
But the derivatives don't. The derivatives are just the R mu.
What do you mean? You mean what?
I'm totally confused. I don't know what we're talking about anymore.
Okay. So what I'm saying is, and we should wrap up in a second. But what I'm saying is, it seems like the derivation would imply that so the first order term in, you know, the size of a geodesic ball of size r, right? The first order term in the sort of polynomial piece is proportional to r mu nu, right?
Second order term.
Second order term, whatever, the first non-zero term.
Yep.
Is proportional to r mu nu. Okay. So now we're saying that the derivation implies that the volume of the geodesic ball doesn't change.
Sure.
Right?
Yep.
And in a first approximation, we can interpret that in continuum space as being the statement that r mu nu is equal to 0.
Yep.
Okay. But now let's consider the higher order terms. The full statement would be r mu nu plus all these weird derivatives of the Riemann tensor is equal to 0.
Why? That's the thing you said. I mean, you said that a couple of times. As I say, I still don't understand what that means.
Okay, because if you look at the volume of a geodesic ball expanded in powers of r, right? Yeah. You get r mu nu, the r mu nu piece, times r squared, plus some big mess of Riemann tensors, r to the fourth.
Yep.
Right? Okay. So the point that I'm making is that the statement that, you know, what is the interpretation in continuum space of the statement that the volume of a geodesic ball is conserved? Answer that this whole power series is equal to 0.
Why?
Not just on what?
Why?
Because that's the volume of the geodesic ball. We just agreed that the volume of the geodesic ball
in the limit as r goes to 0. So without additional convergence criteria, the second order term is all that matters.
No, I realize that. But we're looking at, if we don't take the limit, I mean, we've got a non-uniform.
You don't take the limit, then the volume, you don't have a volume formula.
No, I'm saying, look, the problem is a non-uniform convergence problem in the end. Because
yeah, right.
We're interested in
which is why you can't just place, you have to actually analytically justify the limit, what you send to 0.
I understand, but the point that I'm making is that the r, when the r is a singular, right? The capital R is a singular.
Yeah.
Well, I'm confused. I mean, when the capital R is a singular, then isn't there a different limit of this geodesic volume that you should be looking at? Or is it hopeless? I mean,
if you make additional convergence assumptions.
Well, I guess we don't know what the continuum limit is. If capital R is going to infinity, there isn't really a continuum limit in the manifold, an ordinary manifold sense.
Right, but there is if you exclude that point.
Sure.
So I still don't understand. I mean, you can get conditions if you make additional constraints on the convergence rate. But that doesn't seem to be what you're saying. You're saying something else.
I'm saying something else, yeah. But
what you're saying involves taking a limit of a power series as r goes to 0, but somehow keeping the terms that go to 0 faster than the second order term and implying that they somehow contribute equally, which is not.
It's silly. Yes, that's not what I'm trying to say. That's not what I'm trying to say.
Okay.
It's not what I'm trying to say. I'm trying to say, maybe what I'm trying to say is,
those terms have nothing to do with volume, right? Those higher order terms have nothing to do with volume.
What do you mean? They're part of the expansion of the volume of a geodesic ball.
As r goes to 0. So the second order term gives you the volume, and the higher order terms give you the harmonics.
What do you mean by harmonics?
They tell you things about what the geodesic balls look like, not how big they are. right? That's what Weyl curvature means.
Yes, I understand that point. But so when you talk about these higher order corrections, the basic point has to be that they are things that show up. There's one thing that comes out because once you subtract off the small r case, you're going to get some residue. Anyway, we'll talk about this.
Right, exactly.
Yeah.
So what you have to do is not just say the thing limits to 0. You have to make a convergence assumption. You have to say it limits to 0 at such and such a rate.
Yes. Alternatively, you can simply say that little r, I mean, that little r that's asking the scale on which the thing becomes a continuum. I mean, the scale on which the thing stops being continuum, so to speak, is that little r.
Mm-hmm.
So on the scale on which it stops being continuum, the corrections are of order, I would think the ratio, I mean, I would guess it's the ratio of some curvature to the size on which the thing is no longer a continuum.
Yeah, i.e. 1 over the Knudsen number squared.
Well, so the claim is the order of the corrections is distance over which continuum breaks down divided by radius of curvature, basically. Is it that way up or is it the other way up? No, it's the other way up.
Well, it's, as I say, it's 1 over the Knudsen number squared. I.e., 1 over the
what is the Knudsen number? Is the distance, is the mean free path?
It's the ratio of the distance at which the continuum approximation becomes correct to the length of an elementary hyperedge. Take the reciprocal of that square edge.
There's no elementary hyperedges in fluids. I mean, it's the distance.
No, it's the Knudsen number in our expansion, right? That's the mean free path is the point at which the continuum approximation becomes valid. The characteristic length scale is the average length.
Something like that. All right, we should continue another point.
Sure.
Unfortunately, the frustrating thing is that now I really want to. Oh boy, there's so much to figure out here. And I've got all this. I don't know how instantly I'm going to be hit with all kinds of things, of all kinds of company things that I've been putting off for 4 weeks. Well, we'll find out. But physics, we need to carve out some time for physics, especially since, look at this, we may have just solved, another one of my kind of, I should have had these, it's not millennial problems, but you know what I'm saying, these sort of, if we manage to get general purpose robotics out of this thing, it's going to be absolutely absurd.
Right.
I mean, we're getting, we're potentially getting, solving the distributed blockchain problem, which, by the way, we need to come back to. You haven't been much involved in that, but I think you should think about it a bit. Mm-hmm. I mean, I think that it's a
sure.
We need to get Tally also involved. I think between Tally and you and me and Max, I think we might be able to, and somebody from the blockchain world. And by the way, this summer camp student, Igor, did a nice project on the causal graph of Bitcoin, which I think we should look at carefully. And then we're going to discover there's this notion of velocity of money, right?
Mm-hmm. Yep.
I wonder whether there's going to be an energy principle. I wonder whether there's going to be an Einstein's equations in economics.
That would make sense.
It would. Yes, it would. I mean, well, old Albert had a more general idea than one gives him credit for.
Right.
I mean, which in a sense, and I don't think it really had precursors, that idea. I don't know whether that idea had precursors. Anyway, separate question for another day. All right. Good stuff.
Okay.
Okay.
Thanks. All right.
See you later. Okay. Bye-bye.